For years, astronomers have pushed their telescopes to the limits, trying to see farther and deeper into space than ever before, but nothing could have prepared them for what the James Webb Space Telescope recently revealed. It took an image from so far away that it defied every prediction about what should exist in that part of the universe. What exactly did Webb see out there, and why is it rewriting the story of cosmic history? Before we start, let us know in the comments below where in the world you're watching from and what time it is for you now. We're always excited to hear where our viewers are tuning in from. Webb's first deep field was the very first official image taken by the James Webb Space Telescope, also known as JWST. This remarkable picture showed a very tiny area of the sky that can be seen from the southern hemisphere. At the centre of this view is a galaxy cluster called SMACS 0723, which lies in the constellation of Volans. What made this image so special was that it displayed thousands upon thousands of galaxies, some of which are as old as 13 billion years. This means that the telescope captured light that began its journey across space not long after the universe itself was born. It was the most detailed and highest quality image of the early universe ever taken. The image was captured using the telescope's near-infrared camera, also known as NIR-CAM, and was presented to the public by the National Aeronautics and Space Administration, NASA, on the 11th of July in the year 2022. The James Webb Space Telescope itself is one of the most advanced scientific instruments ever created. It was designed and is operated by NASA, with the help of other space agencies, to study the universe using infrared light, a type of light that allows scientists to see objects that are too distant, faint, or hidden by cosmic dust for ordinary telescopes to detect. It was launched into space in December of the year 2021 and has been operating ever since from a special orbit known as the Second Sun-Earth Lagrange Point, or L2. This point is located about 1.5 million kilometers away from our planet, which is roughly 900,000 miles. From there, the telescope moves in harmony with both the Earth and the Sun, keeping the same alignment as it observes the distant cosmos. This unique position gives the telescope a stable view of deep space and keeps its instruments cool, allowing it to detect faint heat signals from faraway galaxies, stars, and planets. The historic first deep field image was created from a series of detailed observations taken by the near-infrared camera. It was not just one single photograph, but a carefully assembled combination of many images taken at different wavelengths of infrared light. Together, these exposures added up to a total of 12.5 hours of observation time. This long exposure allowed the telescope to collect enough faint light from incredibly distant galaxies that would otherwise remain invisible. SMACS 0723, the galaxy cluster at the heart of the image, is located in a part of the sky visible from the southern hemisphere. This cluster had been studied many times before by the Hubble Space Telescope and other observatories. However, none had ever revealed it in such extraordinary depth and detail. The light captured in Webb's image shows the cluster as it appeared around 4.5 billion years ago, meaning that the telescope is allowing us to see the cluster as it was long before Earth even formed into its current state. The area of the sky shown in the image might seem enormous, but in reality, it covers a space that would look about the size of a grain of sand held at arm's length. Despite this tiny patch of sky, the number of galaxies visible in it is astonishing. Many of the galaxies seen in the image appear red or orange in colour because of a phenomenon called redshift. This happens when light waves stretch as they travel across expanding space. Since the universe has been growing larger ever since the Big Bang, the light from faraway galaxies becomes stretched out, making it shift toward the red end of the spectrum. Scientists studying Webb's image have already measured the redshift values for nearly 200 different objects within it, with the most distant one showing a redshift value of 8.498. This means that the light from that galaxy began travelling toward us when the universe was extremely young, only a few 100 million years after its formation. One of the most fascinating aspects of the Webb deep field is how the galaxy cluster acts as a giant cosmic magnifying glass. This effect, known as gravitational lensing, occurs because the combined mass of all the galaxy's gas and dark matter within the cluster bends the space around it. This bending of space distorts and magnifies the light coming from even more distant galaxies located behind the cluster. As a result, the telescope can see galaxies that would otherwise be far too faint to detect. Thanks to Webb's sensitive near-infrared camera, astronomers were able to see incredibly small and dim structures for the first time, including tiny star clusters, faint galaxy shapes, and delicate wisps of light that had never been visible before. When looking closely at the photograph, one can notice 6 bright spikes and 2 fainter spikes radiating from some of the points of light. These are not actual parts of the galaxies, but optical effects caused by the telescope's design. The 6 bright spikes are a result of diffraction, which happens when light waves bend around the edges of the telescope's main mirror. Webb's mirror is made up of 18 separate hexagonal segments that fit together to form a large honeycomb-like surface. Because of this hexagonal shape, light bends in such a way that 6 distinct diffraction spikes appear around bright sources. In comparison, telescopes that use round mirrors or lenses produce circular patterns of light known as airy disks instead of spikes. The 2 fainter horizontal spikes are created by the metal struts that hold the telescope's smaller secondary mirror in front of the large main mirror. There are 3 of these struts, and they cause 6 diffraction spikes. However, 4 of these spikes align perfectly with the 6 bright ones created by the main mirror, leaving only 2 additional fainter spikes visible. These details, while not real features of the cosmic objects, are a natural outcome of Webb's unique and complex optical system. On the 11th of July in the year 2022, the James Webb Space Telescope delivered to humanity what was then the deepest and sharpest infrared image of the universe ever taken. This single photograph represented decades of hard work, planning, and technological progress. It was the first full-color image released from the telescope and offered the clearest infrared view of the cosmos that had ever been captured. When the image was made public, it revealed an overwhelming number of galaxies in what seems like just a small piece of the sky. Webb's powerful infrared vision made it possible to detect extremely faint structures in galaxies that are unimaginably distant, allowing scientists to peer further back in time than ever before. Some of the galaxies shown in the image are among the faintest ever observed in the infrared spectrum, meaning their light has travelled for billions of years before reaching the telescope's detectors. For astronomers, seeing such galaxies is like opening a window into the earliest chapters of the universe's history. It shows how the first generations of galaxies formed, grew, and evolved after the Big Bang. The incredible detail captured by Webb gives researchers clues about how stars and galaxies came together and what conditions might have been like in the first few 100 million years of cosmic time. The release of the first deep-field image was a highly celebrated moment around the world. The photograph was first revealed to the public during a special event on the 11th of July 2022 by the President of the United States, Joseph R. Biden, Jr. The event marked not just a milestone in astronomy, but also a symbolic step for humanity's quest to understand its origins. Scientists, space enthusiasts, and ordinary people alike were amazed by how much detail and beauty could exist in such a seemingly small part of the sky. The image, though just one of many that the telescope will produce, represented the beginning of a new era in our exploration of the universe. With its powerful instruments and precise engineering, the James Webb Space Telescope has been able to uncover secrets hidden in the faintest glimmers of light, stretching back nearly to the dawn of time itself. Webb's first deep field is more than a photograph. It is a glimpse into the ancient universe, a look at the galaxies that formed billions of years ago, and a testament to how far human curiosity and technology have come. Even though it focuses on a spot of sky no larger than a grain of sand, this single image captures the vastness of creation, showing that every corner of the cosmos holds countless worlds, galaxies, and stories waiting to be discovered. Each tiny sparkle in the picture is not just a dot of light, but a distant galaxy filled with billions of stars and perhaps even planets orbiting around them. The depth and richness of Webb's view remind us that the universe is far more immense and full of wonder than we can ever fully grasp. The James Webb Space Telescope continues to observe new regions of space, building on the legacy of this first breathtaking image. Webb's first deep field remains a historic symbol of what humanity can achieve through persistence, creativity, and the desire to look beyond the limits of what we once thought was possible. Through its golden mirrors and unmatched sensitivity, it has turned a tiny speck of the sky into one of the most extraordinary cosmic portraits ever captured, forever changing how we see the universe and our place within it. The Carina Nebula, also known as the Eta Carinae Nebula, and catalogued as NGC 3372, is one of the most breathtaking and complex regions in the entire Milky Way galaxy. It lies deep in the southern constellation of Carina, a part of the vast Carina-Sagittarius arm, and is an enormous mix of glowing gas, swirling dust, and dark, mysterious shapes. This immense cloud of cosmic material sits about 8,500 light-years away from our planet, which means the light we see from it today actually began its journey toward Earth long before human civilization even began. The nebula is a region of incredibly active star formation, packed with massive young stars that are shaping and heating the surrounding clouds with their intense radiation and powerful stellar winds. Inside its wide boundaries is the Grand Carina OB1 stellar association, which contains several open star clusters filled with some of the brightest and most massive stars known. Among these are the clusters named Trumpler 14 and Trumpler 16, both shining examples of how new stars are born and evolve in the universe. Trumpler 14 is especially fascinating because it is one of the youngest known star clusters in our galaxy, estimated to be only about 500,000 years old, a mere blink in cosmic time. Inside this youthful cluster is the brilliant O-type supergiant HD 9329A, a star that radiates with immense power. Trumpler 16, on the other hand, hosts some of the most extreme and luminous stars ever discovered, including the famous WR25 and the legendary Eta Carinae system. In addition to these, there are several other clusters: Trumpler 15, Colander 228, Colander 232, NGC 3324, and NGC 3293, that are also part of the Carina OB1 group. Among these, NGC 3293 stands out as both the oldest and the farthest from Trumpler 14, which suggests that star formation has been taking place here in several waves, continuing across millions of years. When viewed from Earth, the Carina Nebula is one of the largest diffuse nebulae visible in the sky. It stretches across a vast region that makes it roughly 4 times bigger and even brighter than the famous Orion Nebula. Yet, despite its magnificence, it is far less well known because it lies in the southern sky, invisible to most observers in the northern hemisphere. The nebula was first recorded in the mid-18th century, in the year 1752 by the French astronomer Nicolas Louis de Lacaille, who observed it while working at the Cape of Good Hope in South Africa. In modern astronomy, the Carina Nebula has become one of the most closely studied regions in the Milky Way. Its size and brightness make it a perfect laboratory for understanding how stars are born, live, and die. It was also among the first 5 cosmic objects chosen by the James Webb Space Telescope when it began full operations. One of Webb's first detailed images focused on a young star-forming region within NGC 3324, nicknamed the Cosmic Cliffs. This image revealed towering walls of gas and dust that looked almost sculpted by the light and wind of young stars, showing a breathtaking scene of creation on a galactic scale. The nebula's apparent size in the sky measures about 120 by 120 arc-minutes, centered at coordinates corresponding to a right ascension of 10 hours, 45 minutes, and 8.5 seconds, and a declination of 59 degrees, 52 minutes, and 4 seconds south. Modern measurements confirm its distance at about 8,500 light-years, or roughly 2,600 parsecs from Earth. At the heart of this vast region lies its most famous and powerful resident, Eta Carinae. This is not an ordinary star, but a hypergiant, one of the most massive and luminous stars ever studied. Astronomers estimate that Eta Carinae's mass ranges from about 100 to 150 times the mass of our Sun, and it shines with a brilliance nearly 4 million times greater than the Sun's light. Because of its immense size and relative closeness to Earth, Eta Carinae provides scientists with a rare opportunity to study a hypergiant in extraordinary detail. There may be other stars in the universe that are even brighter or heavier, but most of them are too far away for astronomers to observe clearly. Over the years, several candidates for the title of most massive star have appeared, only to be downgraded when better data became available. Even as late as the year 2006, Eta Carinae was still considered to have the highest confirmed luminosity known, based on observations across a wide range of wavelengths. Stars like Eta Carinae are extremely rare and live dangerous lives. A single galaxy as large as the Milky Way might have only a few dozen of them at any given time. When a star has more than 80 times the mass of the Sun, it can emit more than 1,000,000 times as much light. However, with such immense power comes instability. For those with masses greater than 120 times the Sun's, this limit is exceeded, meaning their gravity barely manages to contain their own energy. Such stars are constantly on the edge of tearing themselves apart, and many of them are expected to end their lives in colossal explosions, supernovae or even hypernovae, that can briefly outshine entire galaxies. Eta Carinae's influence on its surrounding nebula is dramatic and easy to see. The strong radiation and stellar winds coming from the hypergiant have sculpted the nearby clouds, creating dark, finger-like globules of gas with tails that point directly away from the massive star. The Carina Nebula we see today looks very different from how it appeared in the early 19th century, before Eta Carinae underwent one of the most powerful eruptions ever recorded in stellar history. During the period known as the Great Eruption, which took place in the 1840s, Eta Carinae expelled an enormous amount of material into space, forming a thick cloud of dust that surrounded the star and dimmed its ultraviolet light. This outburst temporarily made Eta Carinae the second brightest star in the entire sky, only outshone by Sirius. Within the larger Carina Nebula, this explosion created a much smaller but striking feature known as the Homunculus Nebula, which means little man in Latin. The Homunculus Nebula is a fascinating structure that envelops Eta Carinae like a cocoon. It is a small region of ionized gas, known as an H2 region, where the gases are excited and glowing due to the intense radiation from the central star system. Much of the light that Eta Carinae emits is absorbed by the dust in this smaller nebula, and then re-emitted as infrared radiation. Because of this, the Homunculus Nebula is actually the brightest object in the entire sky when viewed at mid-infrared wavelengths. By studying the size and shape of the homunculus, astronomers have been able to calculate its distance and structure with remarkable precision. The most accurate measurements suggest that it lies about 7,660 light-years away from Earth, give or take 160 light-years, or around 2,350 parsecs. The two large lobes of the homunculus extend roughly 22,000 astronomical units from the centre, forming a shape that looks like a pair of giant bubbles joined at the middle. The axis of this structure is tilted about 41 degrees from our line of sight, meaning we observe it from Earth at an angle that is slightly more head-on than side-on. The Keyhole Nebula, often called simply the Keyhole, is a small but striking dark cloud made up of cold gas molecules and cosmic dust. It lies within the grand and glowing Carina Nebula, one of the most spectacular regions in the Milky Way. Against the bright and fiery background of glowing gas, the keyhole appears like a mysterious dark shape, its edges lit up by glowing filaments of hot gas that shimmer and twist in space. The contrast between the dark cloud and the luminous surroundings makes this little region stand out, almost as if nature had carved a secret doorway into the heart of the nebula. The Keyhole Nebula has a fascinating history of discovery and naming. In the early 19th century, the famous astronomer Sir John Herschel was among the first to describe it in detail. He initially called it a lemniscate oval vacuity, a technical term that meant an oval-shaped empty space, and later simply referred to it as the oval vacuity. For many years, scientists continued to use the word lemniscate to describe this oddly shaped part of the Carina Nebula. But in the year 1873, an astronomy writer named Emma Converse described the shape as looking like a keyhole in an article for Appleton's Journal. Her poetic comparison caught on quickly, and soon everyone began calling it the Keyhole Nebula. Over time, the name became so popular that people sometimes used it not only for the small dark cloud itself, but even to describe the entire Carina Nebula, the great glowing region that holds this curious shape within it. The keyhole structure itself stretches across about 7 light-years in diameter, which is roughly 2.1 parsecs. Though it might seem unchanging in the silent depths of space, astronomers have found that its appearance has shifted noticeably since it was first recorded. These changes may be caused by variations in the powerful radiation coming from the enormous and volatile star Eta Carinae, which lies nearby and floods the region with intense energy. Interestingly, the Keyhole Nebula does not have its own official NGC, New General Catalogue, designation. Some have mistakenly identified it as NGC 3324, but that name actually belongs to a separate reflection, an emission nebula situated just to the northwest of the main Carina Nebula, where a different cluster of young stars resides. Within the keyhole itself, there exists a small but striking object known as a Bock globule, a dense pocket of gas and dust where new stars can be born. This particular globule, located at a right ascension of 10 hours 44 minutes 30 seconds and a declination of negative 59 degrees 40 minutes, was photographed in extraordinary detail by the Hubble Space Telescope. Because of its unusual shape, it earned the nickname Carina's defiant finger. In the Hubble images, light can be seen gleaming along its edges, especially near the southern tip, where the finger points upward into the surrounding glow. Astronomers believe that this globule is being ionized by powerful nearby stars, possibly the massive Wolf-Rayet star WR25 and a bright blue supergiant known as Trumpler 16244. The globule itself has an estimated mass of at least 6 times that of our Sun, and there may be young stars forming within it right now. However, its fate is already written. Intense radiation from surrounding stars will eventually destroy it completely, evaporating it away within the next 200,000 to 1 million years, which is an instant in cosmic terms. Nearby in the Carina Nebula lies the open star cluster known as Trumpler 14. It spans about 6 light-years, or roughly 1.8 parsecs across. Trumpler 14 is one of the most prominent clusters inside the Carina Nebula and is located around 8,000 light-years, or about 2,500 parsecs from Earth. This cluster is filled with youthful, brilliant stars. About 2,000 of them have been identified so far, and the combined mass of all these stars together is estimated to be about 4,300 times the mass of the Sun. These stars shine intensely, lighting up the clouds of gas and dust around them, and together they help shape the breathtaking scenery of the nebula. Another cluster in this great cosmic region is Trumpler 15, which lies on the northeastern edge of the Carina Nebula. For a long time, astronomers debated how far away it was, as different studies produced different estimates. However, with precise new data from the European Space Agency's Gaia mission, scientists have confirmed that Trumpler 15 lies at roughly the same distance as the other clusters of the Carina OB1 stellar association, meaning it truly belongs to the same massive family of stars. Trumpler 16 is another of the main clusters within the Carina OB1 association, and is both larger and more massive than Trumpler 14. This cluster is especially famous because it contains one of the most remarkable stars ever observed, Eta Carinae. This star, known for its unpredictable outbursts and enormous brightness, dominates its surroundings and floods the nebula with light and energy. The radiation from Eta Carinae has a powerful influence on nearby structures like the Keyhole Nebula, shaping and changing them over time. Another awe-inspiring feature of the Carina Nebula is something astronomers call Mystic Mountain. This poetic name refers to a towering pillar of gas and dust that was photographed by the Hubble Space Telescope in celebration of its 20th anniversary. The image, captured on the 1st and 2nd of February in the year 2010 by Hubble's Wide Field Camera 3, revealed a vast structure about 3 light-years tall, nearly 1 parsec in height. Inside this majestic column, new stars are being born. As these infant stars ignite, they release jets of gas that shoot out from the peaks of the pillar, sculpting the surrounding clouds into breathtaking shapes that glow under the light of nearby massive stars. The Carina region is also home to some extraordinary stars with extreme physical properties. One of them, WR22, is an eclipsing binary system, meaning that 2 stars orbit each other in such a way that one periodically passes in front of the other, from our point of view, causing their combined brightness to dim and brighten rhythmically. The masses of these 2 stars have been estimated in different ways, but they are both immensely heavy. The primary star's mass is thought to range between 60 and 70 or more times that of the Sun, while the secondary star's mass is between 21 and 27 solar masses. Other studies have even calculated the primary's mass at 74 or 78 times that of the Sun, making it one of the most massive stars known. Another key star system, WR25, lies near the centre of the Carina Nebula and is a member of the Trumpler 16 cluster. The main star in this system is a Wolf-Rayet star, one of the most luminous types of stars in our galaxy, shining with a brilliance millions of times greater than that of the Sun. Its companion star is much harder to detect but is believed to be a bright OB-type star, also very hot and luminous. Together they represent one of the most energetic binary systems known, contributing greatly to the intense radiation environment of the Carina Nebula. Then there is HD 93129, a spectacular triple-star system made up of O-class stars, which are among the hottest and brightest stars in the universe. All three members of this system rank among the most luminous stars in the entire Milky Way. The system consists of two major components, HD 93129A and HD 93129B, while HD 93129A itself is actually a close pair of two stars. HD 93129A has been resolved into two components. The brighter of the pair dominates the light we see, although its companion is only about 0.9 magnitudes fainter. The brighter component, HD 93129AEL, is an O2 supergiant, one of the hottest and most massive types of stars known, while its companion, HD 93129AB, is an O3.5 main sequence star. Over the years, astronomers have observed that the distance between them is slowly shrinking, from about 55 milliseconds in the year 2004 to only 27 milliseconds in the year 2013, suggesting a Titan dynamic orbit, though it has not yet been fully mapped. The nearby star HD 93129b, located about 3 arcseconds away from the inner pair, is an O3.5 main sequence star as well. It is around 1.5 magnitudes fainter than the combined brightness of HD 93129a, and its luminosity is roughly the same as that of HD 93129ab. Altogether, this triple system forms one of the brightest beacons within the Carina Nebula's rich and crowded star field. Another brilliant star in the area is HD 93250, one of the brightest objects in the Carina Nebula's sky. It lies only about 7.5 arc-minutes from Eta Carinae, and is thought to belong to the same general star cluster, Trumpler 16, though it appears slightly closer to the compact cluster Trumpler 14. HD 93250 is itself a binary star, though the individual stars have never been directly separated in observation. Nevertheless, astronomers believe that both components are extremely similar in their properties. Over time, different studies have assigned it various spectral classifications, ranging from O5 and O6 and 7 to O4 and even O3. Some have described it as a main sequence star, others as a giant star, showing how complex and variable such systems can be. In more recent classifications, HD 93250 has been chosen as the standard example for a newly defined spectral category, known as the O4 subgiant class, created by the Galactic O-star spectroscopic survey. This makes it a reference point for future studies of similar stars. HD 93205 is a remarkable double-star system made up of two enormous and intensely bright stars that orbit around a shared centre of gravity. These two stars are bound together by gravity, yet each is a powerful force of nature on its own. The larger and more dominant of the two stars belongs to the stellar class known as type O 3.5 on the main sequence. This means it is extremely hot, shining with a blue-white brilliance and burning its fuel at an extraordinary rate. When astronomers studied its spectrum, the unique pattern of light it gives off, they discovered the presence of glowing lines of ionized nitrogen and helium. These special lines reveal that material created deep inside the star, the products of nuclear fusion, has been brought up to the surface. This is likely the result of powerful internal mixing within the star's massive turbulent layers. The same spectrum also indicates the presence of a strong stellar wind, meaning that the star constantly blows vast amounts of gas and particles out into space at tremendous speeds. By carefully studying the movement of the stars and the slow twisting of their orbit, known as apsidal motion, scientists estimated the mass of this dominant star to be between 40 and 60 times the mass of our own Sun. Even though this is a huge amount, it is still slightly smaller than what would normally be expected from models of how such massive stars evolve, given its brightness and temperature. This small difference makes HD 93205 an especially interesting object for astronomers trying to understand the lives of the universe's most massive stars. The companion star in the system is smaller, but still incredibly massive when compared to most stars in the galaxy. It belongs to the O8 spectral type, also on the main sequence, which means it is still in the long, stable part of its life, where hydrogen is being fused into helium in its core. The mass of this second star is estimated to be about 20 times that of the Sun, making it far more powerful and luminous than even the brightest stars visible from Earth without a telescope. This smaller star travels around its larger companion at a truly astonishing speed, more than 300 kilometers every second, which is about 190 miles per second. At such a high velocity, the effects of Einstein's theory of relativity become noticeable, making HD 932051 one of the rare examples of what scientists call a relativistic binary system. In such systems, the gravitational effects predicted by relativity cause the orbit itself to slowly shift and rotate in a way that can be measured and predicted with great precision. The Pillars of Creation is one of the most famous and mesmerizing astronomical photographs ever captured by humanity. It was taken by the Hubble Space Telescope, an orbiting observatory that has transformed our understanding of the universe since it was launched into space in the early 1990s. The image shows towering, finger-like columns made of interstellar gas and dust. These massive structures rise within a region of space known as the Eagle Nebula, which lies in the constellation of Serpens, about 6,500 to 7,000 light-years away from our planet Earth. In simpler terms, what we are seeing in this photograph is a vast nursery of stars, a place where new suns are being born amid clouds of cold gas and dust that stretch for many trillions of kilometers across space. The name Pillars of Creation itself carries a deep meaning. These columns are called pillars because they appear like great towers rising out of the nebula, and of creation because they are literally creating new stars within them. Yet, while these same towers are forming new stars, they are also being slowly destroyed by the radiation of nearby recently formed stars. The intense light and heat from those young stars carve away the gas and dust, eating into the very material that forms new ones. It is a cycle of creation and destruction taking place on a cosmic scale, one of the most beautiful and dramatic processes in the entire universe. The structures themselves were first discovered long before Hubble photographed them. In the year 1920, an astronomer named John Charles Duncan identified these dark columns of gas on a photographic plate taken with the 60-inch telescope at the Mount Wilson Observatory in California. At that time, astronomers had only just begun to explore the vast structure of our galaxy and had no idea that such mysterious and majestic clouds could give birth to stars. It would take many more decades of technological progress before humanity could see these elephant trunks in all their astonishing detail. Then, on the first day of April in the year 1995, the Hubble Space Telescope captured the now legendary image. The astronomers Jeff Hester and Paul Scowen from Arizona State University were responsible for planning and processing the photograph. The image instantly became one of the most recognized and celebrated views ever taken of the cosmos. It was later named one of the top 10 photographs ever captured by Hubble, according to the astronomy website space.com. The photograph shows 3 towering columns of gas and dust, each stretching several light-years in length. To understand the scale, 1 light-year is the distance that light travels in a single year, roughly 10 trillion kilometers. This means that each of these pillars could easily swallow our entire solar system many times over. The leftmost pillar is about 4 light-years long, nearly 25 trillion miles. At the top of these pillars are finger-like extensions known as evaporating gaseous globules, or eggs for short. Each egg contains dense pockets of gas that act as incubators for newborn stars. Inside these hidden pockets, gravity pulls matter together until nuclear fusion ignites, creating new suns. As these infant stars grow hotter and brighter, they begin to burn away the gas surrounding them. Eventually, they burst out from their cocoon of dust, leaving behind glowing regions of ionized gas and trailing wisps that mark their emergence into the wider galaxy. The colour in the photograph is not what the human eye would see in space. Instead, it is a composite of 32 separate images, captured through different filters on Hubble's Wide Field and Planetary Camera 2, often called WFPC-2. Each filter isolates light emitted by specific elements in the gas. Hydrogen glows green, sulfur appears red, and oxygen shines blue. When these different wavelengths are combined, they produce the breathtaking, almost surreal colours that made the image so famous. The bright edges of the pillars show where ultraviolet light from nearby stars is striking the gas, heating it, and causing it to glow. Interestingly, the photograph has a small missing portion in the top right corner. This is not an error, but a feature of Hubble's camera system. The top right quadrant of the WFPC-2 camera had a magnified view, and when the images were scaled to match the others, a small gap appeared, creating a kind of stair-step pattern. This quirk is visible in many Hubble photographs and depends on how the image is oriented for publication. After its release in 1995, the Pillars of Creation became a global cultural icon. It was featured in countless magazines, documentaries, and educational programs, and it quickly became one of the defining images of modern astronomy. National Geographic even noted that 2 decades after its release, the photograph had been printed on everything from t-shirts to coffee mugs. The phrase, Pillars of Creation itself, comes from an old sermon delivered in the year 1857 by the preacher Charles Spurgeon, titled The Condescension of Christ. Though Spurgeon used the phrase in a religious context, it found new life in the scientific world as a poetic name for one of the most awe-inspiring cosmic scenes ever recorded. But the story of the Pillars did not end there. Astronomers continued to observe and study this region using newer telescopes across different wavelengths of light. In the year 2001, the Chandra X-ray Observatory, a space telescope designed to detect X-rays from energetic celestial sources, observed the same region. It did not detect many X-ray sources within the towers themselves, suggesting that there were not many very young massive stars there emitting strong radiation. However, Chandra did detect X-rays from other young stars scattered throughout the area, confirming that star formation was actively taking place nearby. In the year 2007, data from Chandra's earlier observations were released to the public, giving scientists a new way to look at the region. Meanwhile, in 2010, the Herschel Space Observatory, operated by the European Space Agency, captured images of the Pillars of Creation in far infrared light. Unlike visible light, infrared radiation can pass through thick clouds of dust, allowing astronomers to peer inside the columns and study the dense cores where new stars are being born. These observations helped scientists understand not only how stars are formed within these clouds, but also how the ultraviolet light from nearby stars sculpts and erodes them over time. The most detailed new view came in January of the year 2015, during the 25th anniversary celebration of the Hubble Space Telescope's launch. Astronomers unveiled a much larger, sharper, and higher resolution version of the original photograph. This new image was taken with Hubble's Wide Field Camera 3, which had replaced the older WFPC-2 during a space shuttle mission in the year 2009. The updated photograph showed even more detail at the base of the pillars and revealed many new features, including faint stars that were hidden in the older image. An infrared version of the same region was also released, allowing viewers to see through the thick dust and glimpse the stars forming inside. But before Hubble's second image, astronomers using NASA's Spitzer Space Telescope had made a surprising discovery. Spitzer, which observes the universe in infrared light, detected a strange cloud of hot dust near the Pillars of Creation. The shape and temperature of this cloud led some scientists to speculate that it could be the aftermath of a supernova explosion, the violent death of a massive star. They suggested that the shockwave from the explosion might have already swept through the region about 6,000 years ago, potentially destroying the pillars. However, because the pillars are around 7,000 light-years away from Earth, the light from their destruction would not reach us for another 1,000 years. In other words, what we see today could be a ghost image of structures that no longer exist. This interpretation, however, was not universally accepted. Other astronomers argued that if a supernova had indeed occurred nearby, there should be far stronger emissions of radio waves and X-rays than were actually observed. They proposed a different explanation, that powerful stellar winds from massive nearby stars could have heated the dust, creating the same appearance without requiring a supernova. If this alternative is correct, the Pillars of Creation are not yet gone but are slowly being eroded over time by the relentless radiation from young stars. As technology advanced, astronomers continued to revisit the famous pillars with ever more powerful instruments. In October of the year 2022, the James Webb Space Telescope, the most advanced observatory ever built, captured an extraordinary new image using its near-infrared camera, NIRCam. The Webb telescope revealed countless young stars still forming within the pillars, seen as small glowing red spots near the edges of the towers. These are stars in the earlier stages of their lives, still surrounded by the dust and gas from which they were born. Webb's image also displayed the intricate texture of the gas clouds in exquisite detail, with fine filaments and wisps never before visible. In June of the year 2024, NASA released a brand new visualization of the Pillars of Creation, a three-dimensional rendering created using data from both the Hubble and James Webb telescopes. This virtual model allows viewers to explore the pillars from multiple perspectives, as though flying through them in space. NASA described this digital creation as the most comprehensive and detailed multi-wavelength movie yet of this star-birthing region. It combines visible light, infrared, and other wavelengths to create a full layered view of how stars form, evolve, and shape their surroundings. The story of the cameras used to capture these images is also remarkable. The Wide Field and Planetary Camera 2, WFPC-TEBU, which took the original 1995 photograph, was one of Hubble's most important instruments. It was built with 4 separate sensors, known as charge-coupled devices or CCDs. These detectors collected light from the telescope's mirrors and turned it into digital images. After serving for many years, WFPC-2 was replaced by the Wide Field Camera 3 in the year 2009 during Space Shuttle mission STS-125. The older camera was brought back to Earth and is now preserved in a museum, allowing people to see the instrument that gave humanity one of its most beloved views of the universe. The Eagle Nebula, where the pillars of creation are located, is a large cloud of gas and dust within our Milky Way galaxy. It lies in a part of the galaxy called the Carina Sagittarius Arm. The entire nebula is a stellar nursery filled with hundreds of new stars in various stages of formation. The bright light from these young, massive stars ionizes the surrounding gas, causing it to glow with a soft, colourful radiance. The darker regions, such as the pillars themselves, are areas where thick clouds of dust block the light behind them, creating the distinctive shapes that we see in the photographs. Each pillar contains within it many smaller clumps of gas that will one day collapse under their own gravity to form new stars and possibly even planetary systems. The pressure from the ultraviolet radiation of nearby stars compresses some areas of the gas, while simultaneously blowing away the outer layers. Over time, this delicate balance of forces sculpts the clouds into the dramatic finger-like forms that have captivated scientists and the public alike. The finger-like protrusions at the top of the pillars are particularly interesting. Each one is many times larger than our solar system, and they act as protective shields for the material behind them. The dense eggs at their tips absorb most of the ultraviolet radiation, casting long shadows and allowing new stars to form in the relative safety of the shaded regions. As time passes, the eggs themselves evaporate, revealing the newly born stars within. It is an ongoing process, slow and majestic, that unfolds over tens or even hundreds of thousands of years. The composition of the gas within the pillars is mostly cool molecular hydrogen, mixed with small amounts of dust and other elements like carbon, oxygen, and sulfur. The temperatures within the densest parts of the clouds are extremely low, often just a few tens of degrees above absolute zero. Despite this coldness, the gravitational pull within these dense knots of gas is strong enough to ignite the fires of nuclear fusion once the material collapses. From these small beginnings, entire star systems are born. The pillars are constantly being reshaped by photoevaporation, a process where intense ultraviolet radiation from nearby hot stars strips away the gas. The light breaks apart the molecules in the upper layers, heating the gas and causing it to escape into space. This slow erosion gives the pillars their sculpted, almost carved appearance. Over the course of many millennia, the structures will gradually fade away as the gas is dispersed into the surrounding nebula. The instruments aboard Hubble and other space telescopes have made it possible to study this process in remarkable detail. Scientists can track changes in the brightness and structure of the pillars over time, allowing them to measure how quickly the gas is being lost and how star formation continues within the dense cores. These studies help astronomers understand how stars like our Sun might have formed billions of years ago within similar clouds. The combined use of visible light, infrared, and X-ray observations has provided an incredibly rich picture of this region. Each wavelength reveals a different aspect of the process. Visible light shows the glowing outer surfaces of the pillars, infrared light penetrates the dust to uncover hidden stars, and X-rays highlight the energetic regions where young stars release powerful radiation. Together they tell the story of cosmic creation, how light and darkness, heat and cold, destruction and birth are all part of one continuous cycle. The Cartwheel Galaxy, which is listed in astronomical catalogues as ESO 350-40, and also known as PGC 2248, is one of the most remarkable and visually stunning ring galaxies ever observed. It lies roughly 500 million light-years away from Earth, in the southern constellation known as Sculptor. Astronomers classify it as a lenticular ring galaxy, meaning that it shows both the smooth, disk-like appearance of a lenticular system and the distinct circular structure that marks the presence of an expanding ring of stars, gas, and dust. The galaxy has a measured isophotral diameter, meaning the apparent size at a certain brightness level, of about 57.69 kiloparsecs, which corresponds to approximately 188,200 light-years across. The estimated total mass of this vast system falls somewhere between about 2.9 and 4.8 billion times the mass of our own Sun, making it a massive yet dynamically complex structure whose outer ring rotates with a circular velocity of roughly 217 kilometers per second. The discovery of the Cartwheel Galaxy dates back to the year 1941, when the Swiss astronomer Fritz Zwicki first identified it while studying deep photographic plates. Zwicki was a pioneering and sometimes controversial figure in 20th century astronomy, known for his unconventional ideas and for being one of the first scientists to propose the existence of dark matter. Upon seeing the peculiar structure of the Cartwheel Galaxy, Zwicki described it as one of the most complicated stellar systems known, and stated that it was awaiting explanation based on the laws of stellar dynamics. His prediction turned out to be accurate because decades later, the Cartwheel would become a textbook example of how powerful galactic collisions can reshape galaxies into spectacular ring-like forms. Later measurements, including those compiled in the third reference catalogue of bright galaxies, known by the abbreviation RC3, confirmed the exceptional dimensions of the Cartwheel. According to this catalogue, the galaxy has a D25 isophotral diameter of about 60.9 arcseconds, which translates to approximately 57.69 kiloparsecs, or 188,200 light-years, based on its redshift-derived distance of about 132.2 megaparsecs, equal to 431 million light-years. This means that the Cartwheel is slightly larger than the Andromeda Galaxy, which itself is already one of the largest members of our local group. The Cartwheel Galaxy is not an isolated system. It is actually the dominant member of a small galactic group, known collectively as the Cartwheel Galaxy Group. This group contains 4 galaxies that are physically associated and interact gravitationally. The Cartwheel sits at the centre, while its 3 companions orbit or drift nearby. Astronomers refer to these 3 smaller galaxies as G1, G2, and G3. Galaxy G1 is a smaller, irregular blue Magellanic spiral that resembles the satellite galaxies of the Milky Way. Galaxy G2 is a yellowish compact spiral system that features a distinctive tidal tail, a stream of stars and gas stretched out by gravitational forces. Galaxy G3 lies farther away and is usually seen in wide-field images as a more distant spiral. Together, these galaxies form a dynamic neighbourhood where gravitational interactions are frequent and dramatic. Only one supernova has been observed in the Cartwheel Galaxy so far. This stellar explosion, officially named Supernova 2021 AFDX, was a Type II supernova detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, on the 23rd of November in the year 2021. The recorded apparent magnitude of this supernova was about 18.796, meaning it was very faint and required powerful telescopes to be observed. The detection of such an event in a galaxy so far away demonstrates the sensitivity of modern observatories and the continuing activity within the Cartwheel's star-forming regions. The overall structure of the Cartwheel Galaxy is extremely complex and disturbed, making it a fascinating object for astronomers who study galactic evolution. Its visible form consists mainly of 2 major rings. The outer ring, which gives the galaxy its famous wheel-like appearance, is a site of intense and ongoing star formation. This star formation is triggered by the compression of interstellar gas and dust caused by a propagating shockwave. Inside this outer ring lies the inner ring, which surrounds the galaxy's central region, or nucleus. Between these 2 rings, a dark band of dust absorbs light, forming a nuclear dust ring that stands out in high-resolution images. Several faint yet well-defined optical structures, often described as spokes, connect the outer and inner rings, creating the appearance of a wheel with a hub and spokes. Observations at different wavelengths reveal that there are both non-thermal radiocontinuum spokes and optical spokes, although they do not exactly overlap, suggesting that different physical processes create them. The history of the Cartwheel Galaxy suggests that it was once a normal spiral galaxy before undergoing a dramatic transformation. Astronomers believe that several 100 million years ago the Cartwheel experienced a head-on collision with a smaller galaxy that passed directly through its disk. This type of impact is sometimes described as a bullseye collision because of its direct central trajectory. The collision likely occurred between about 200 million and 300 million years before the time at which we now observe the galaxy. When the intruding galaxy plunged through the Cartwheel, its immense gravitational force sent out a powerful shockwave through the gas and dust in the larger galaxy's disk. This expanding shockwave compressed material as it moved outward, triggering an enormous wave of star formation that lit up the galaxy's outer regions while leaving the inner core relatively undisturbed. This process explains why the Cartwheel's outer ring glows with a bluish colour, which comes from the presence of large, hot, young stars that emit bright blue light. These massive stars form rapidly and live short lives, so their colour marks regions where star formation is happening most actively. As the wave of star formation spreads outward, it creates the visual impression of a bright expanding ring moving through space. Astronomers also note that the Cartwheel appears to be slowly reorganising itself back into a more typical spiral shape, with new arms beginning to form and extend outward from the central region. These developing arms are often referred to as the galaxy's spokes, a fitting name given the structure's overall resemblance to a cosmic wheel. In addition to the collision theory, scientists have proposed other explanations to account for the Cartwheel's unusual shape. One such model is based on what is known as gravitational Jeans instability, which describes how certain regions of a galaxy's disk can become unstable under their own gravity and collapse to form new structures. In this scenario, both axisymmetric, meaning circular or radial, and non-axisymmetric, meaning spiral or isometric, gravitational perturbations could lead to the growth of clumps of matter that eventually form ring-like and spoke-like patterns. However, when astronomers compare this theoretical model with actual observational data from the Cartwheel, they find that it does not fully explain the specific details seen in this galaxy, making the collision hypothesis far more convincing. When viewed in deep images, the Cartwheel often appears alongside three nearby galaxies, but radio observations reveal that a fourth companion, the same galaxy G3 mentioned earlier, is physically connected to the Cartwheel through a long tail of neutral hydrogen gas. Neutral hydrogen, also called H1 gas, is the most abundant form of atomic hydrogen in the universe and is often used to trace interactions between galaxies. The presence of this hydrogen tail indicates that G3 is gravitationally linked to the Cartwheel and is likely the true bullet galaxy that caused the collision. This conclusion fits the observed structure and the estimated age of about 300 million years for the ring, which matches the time required for the shockwave to expand to its current size. While galaxies G1 and G2 are located closer to the Cartwheel today, their positions suggest that they were not the original colliders. The greater distance of G3, roughly 88 kiloparsecs, or about 287,000 light-years, from the Cartwheel's centre, aligns better with the dynamics expected of a galaxy that has already passed through and moved away. The study of the hydrogen tail is crucial in confirming this, because gas tails can provide evidence of the direction, speed, and nature of past galactic interactions. Mapping of hydrogen gas has become one of the most important tools in modern astrophysics for identifying the galaxies responsible for major collisions. Hydrogen is light and easily stripped away from galaxies by gravitational forces during close encounters. This process is seen in other galaxies such as the Jellyfish Galaxy and the Comet Galaxy, both of which are experiencing a phenomenon called RAM pressure stripping. In such cases, as galaxies move rapidly through a dense environment like a galaxy cluster, the pressure of the intracluster medium removes their gas, creating long trailing streams that resemble jellyfish tentacles. In the case of the Cartwheel, however, the gas distribution suggests a different type of interaction. Instead of trailing behind, much of the hydrogen gas forms leading tails, consistent with the behaviour seen when two galaxies collide directly, rather than through the gradual stripping caused by a surrounding cluster. During such collisions, the gravity of the smaller bullet galaxy pulls gas and stars from the larger system, creating elongated bridges and tails in the direction of its motion. This leading dominant structure is a hallmark of collision-driven ring galaxies, setting them apart from galaxies affected primarily by environmental stripping. Astronomers studying the future of the Cartwheel Galaxy predict that its current appearance is only temporary on cosmic timescales. Over the next few 100 million years, the structure is expected to change dramatically. The outer ring, which is currently bright and full of young stars, will gradually lose energy and disintegrate as the material within it slows down and begins to drift back toward the galaxy's centre. As the remaining gas, dust and stars fall inward, the cartwheel may regain a more typical spiral form, with density waves re-establishing organised spiral arms. This evolution will depend strongly on whether its companion galaxies G1, G2 and G3 remain at a safe distance. If another collision occurs, the transformation could be delayed or altered entirely. The striking wheel-like shape of the Cartwheel Galaxy, often seen in both optical and infrared images, continues to fascinate astronomers. It serves as a vivid example of how energetic and creative the universe can be in shaping galaxies. The luminous ring surrounding the centre is not a static feature but a dynamic wavefront of star formation. As the expanding shock front moves outward, it compresses the interstellar medium and triggers the birth of clusters of massive stars. These newly formed stars shine brightly, producing ultraviolet radiation that excites surrounding gas and makes it glow. In many ways, the cartwheel functions as a natural laboratory for studying how stars form under extreme conditions. The intense pressure and turbulence created by the collision cause star formation to occur much faster and on a much larger scale than in calm, undisturbed galaxies. This is why galaxies like the Cartwheel are often described as starburst galaxies. In a starburst, vast numbers of stars are born over a relatively short period of time, consuming large amounts of gas. Among these stars are some of the most massive and luminous types, which burn their fuel rapidly and end their lives in spectacular explosions known as supernovas. When such massive stars die, they collapse under their own gravity and form compact remnants, either neutron stars or black holes, depending on their initial mass. Because the Cartwheel's outer ring has recently produced many massive stars, it now contains a correspondingly large population of these remnants. Some of these neutron stars and black holes are found in binary systems, where they orbit closely with a companion star. As the compact object pulls matter from its partner, the infalling gas heats up and emits powerful X-rays. Observations from X-ray telescopes have revealed that the Cartwheel Galaxy contains an unusually large number of these X-ray sources, including both ultra-luminous and hyperluminous types. The brightest of them are thought to be black holes that are accreting material from nearby companion stars. In X-ray images, these systems appear as small white dots concentrated along the outer rim of the galaxy. Their abundance supports the idea that the Cartwheel is undergoing a major burst of star formation, since such objects form most readily in regions rich in young, massive stars. The study of these X-ray sources also provides insight into the life cycles of stars and the effects of collisions on galactic evolution. Each of these high-energy systems represents the end product of a once massive star, linking the processes of birth and death within the galaxy's dynamic environment. In this way, the Cartwheel Galaxy not only illustrates the destructive power of galactic collisions, but also their creative side, how they can trigger the formation of new stars, clusters, and even black holes. Detailed spectroscopic observations of the Cartwheel have revealed further evidence of the violent processes at work. The outer ring shows strong emission lines from ionized hydrogen and oxygen, typical of regions filled with hot, young stars and nebulae. Infrared observations, meanwhile, show the presence of warm dust heated by these stars. Radio studies reveal both thermal and non-thermal emission, indicating that synchrotron radiation from cosmic rays is also present. This combination of data across the electromagnetic spectrum paints a picture of a galaxy in transition, one where past destruction and current creation coexist. The gravitational interactions that shape the Cartwheel have also likely affected its smaller companions. Galaxies G1, G2 and G3 show signs of tidal distortion, with stretched arms and disrupted structures. These features are common in systems where multiple galaxies are bound together and frequently influence each other. The long-term evolution of the entire group will depend on the balance between their mutual gravitational attraction and the momentum from their past interactions. Over billions of years, they may merge completely, forming a single large elliptical or lenticular galaxy. For astronomers, the Cartwheel Galaxy continues to serve as a remarkable example of how galactic collisions can produce intricate and beautiful structures. Its study has helped refine models of ring galaxy formation and shed light on the physics of interstellar shockwaves. Simulations using supercomputers show that when a smaller galaxy collides head-on with a larger spiral, it can send circular waves of density through the larger galaxy's disk. These waves act much like ripples in a pond, compressing gas and creating bright rings that expand outward over time. The Cartwheel provides real observational proof that such mechanisms occur on a galactic scale. In addition to its scientific importance, the Cartwheel has captured public imagination because of its appearance. Its shape truly resembles a cosmic wheel floating in the depths of space, a luminous circle of blue stars surrounding a darker core. High-resolution images taken by the Hubble Space Telescope and later by the James Webb Space Telescope show the astonishing detail of its structure, including the faint spokes and the clumpy regions of new star formation along the rim. These images also reveal the contrasting colours of the galaxy's different components: the bluish outer ring, the yellowish central region, and the darker dust lanes that weave between them. The Cartwheel Galaxy demonstrates how interactions between galaxies are a key driver of evolution in the universe. Rather than being rare accidents, such collisions are common throughout cosmic history. In fact, our own Milky Way is expected to undergo a similar large-scale collision with the Andromeda Galaxy in about 4 billion years, potentially producing structures not unlike those seen in the Cartwheel today. By studying galaxies like the Cartwheel, astronomers gain a glimpse into both the past and future of galactic transformation. Because the Cartwheel lies about 500 million light-years away, the light we see from it today began its journey long before humans existed on Earth. The events we observe, the aftermath of a collision, the glowing ring of new stars and the scattered remnants of older structures, all occurred hundreds of millions of years ago. In cosmic terms, this is relatively recent, but for us, it provides a window into a dynamic and ever-changing universe where creation and destruction are inseparably linked. Far away in the depths of the night sky, there exists a small but fascinating galaxy known as Zwicki 18. It belongs to a special group of galaxies called blue compact dwarfs, and it also carries the rare title of a Wolf-Rayet galaxy, which means it contains extremely hot and massive stars that release powerful stellar winds. This curious system is located at an enormous distance of about 18.44 megaparsecs, which is roughly equal to 60.14 million light-years, in the constellation known as Ursa Major, the Great Bear. It is a tiny and young-looking galaxy shining with a striking blue colour, surrounded by faint gas clouds that mark regions where new stars are being born. The discovery of Zwicki 18 dates back to the early 20th century, when the Swiss astronomer Fritz Zwicki identified it while carrying out a photographic survey of galaxies during the 1930s. Zwicki was known for his sharp eyes and bold ideas about the universe, and even though he could not have known at the time, his discovery would one day become one of the most studied dwarf galaxies in astronomy. Over the decades, this little blue galaxy has drawn the attention of scientists from all over the world because it seems to show what galaxies might have looked like in the distant early universe. The Zwicki 18 is not only small and bright, but also incredibly active at its centre. Astronomers have found that it contains what is called an active galactic nucleus, meaning there is a powerful source of energy in its heart, probably related to a compact and energetic object like a black hole or a dense cluster of massive stars. Observations from ground-based telescopes, particularly from the famous Palomar Observatory in California, began to reveal more about the galaxy around 40 years ago. Back then, astronomers thought that Zwicki 18 had begun its burst of star formation billions of years later than most of its cosmic neighbours. This was very unusual because galaxies with such youthful appearances were normally seen only in the farthest corners of the cosmos, at times when the universe itself was still very young. When the Hubble Space Telescope was launched and started observing Zwicki 18, its clear images seemed to confirm this puzzling idea. Early data from Hubble suggested that the galaxy could be only about 500 million years old, which is incredibly young compared to the age of most galaxies in the nearby universe. If this were true, it would mean that Zwicki 18 somehow managed to delay its formation for nearly the entire history of the cosmos, only coming to life relatively recently. This discovery challenged many existing ideas about how galaxies evolve, because astronomers had long believed that galaxies of this kind had stopped forming billions of years ago. The very existence of such a young-looking system in our cosmic neighbourhood seemed to contradict the traditional understanding of galaxy formation. Scientists proposed several theories to explain what made Zwicki 18 so different. In models of the universe dominated by cold, dark matter, astronomers have predicted that some small dwarf galaxies could still form relatively late. However, those galaxies would be extremely faint, much dimmer than Zwicki 18. Because of this, researchers began to suspect that even though the galaxy looked young, it might not actually be young at all. Perhaps it was only its outer appearance that made it seem youthful, while its true history stretched back far longer than the first estimates had suggested. To explore this mystery further, scientists continued to observe Zwicki 18 using the Hubble Space Telescope, and over time the improved sensitivity of Hubble's instruments allowed them to detect much fainter and older stars hidden among the younger ones. These faint stars revealed something surprising. Zwicki 18 was not newly born at all. It had an older population of stars that must have formed at least 1 billion years ago, and possibly as far back as 10 billion years ago. This meant that the galaxy had likely formed around the same time as most other galaxies in the universe, during the early stages of cosmic history. The earlier assumption that it was a recently formed system turned out to be mistaken, although its appearance continued to make it stand out as a very unusual galaxy. The reason Zwicki 18 looks so young today lies in its low rate of star formation during most of its life, followed by a sudden and intense burst of new star creation in recent times. Spectroscopic observations, which study how light is spread out into its different colours, showed that the galaxy's composition is almost entirely made up of hydrogen and helium, the two simplest and most abundant elements created in the Big Bang. Heavier elements, which astronomers often call metals, are very rare in this galaxy. This is important because metals are usually produced in large quantities by several generations of stars over long periods of time. The fact that Zwicki 18 has so few of them shows that it did not form many stars until quite recently. Its chemical makeup is therefore considered almost primordial, a direct link to the early days of the cosmos. Because of this simple and ancient composition, Zwicki 18 has become one of the most studied dwarf galaxies in existence. NASA's most powerful observatories have all turned their eyes toward it. The Spitzer Space Telescope examined its infrared glow, revealing the distribution of dust and warm gas inside it. The Chandra X-ray Observatory studied its high-energy regions, detecting the presence of hot gas and possibly remnants of exploded stars. The Far Ultraviolet Spectroscopic Explorer, often called FUSE, helped scientists look at the ultraviolet light from its most massive young stars, and more recently, the James Webb Space Telescope began to peer even deeper into its core, revealing details that were never visible before. Yet even after all these observations, the mystery remains. Why did this galaxy form so few stars for so long, and why is it now suddenly filled with new starbirth activity? In the year 2015, another exciting discovery was made about Zwicki 18. Astronomers found an unusually large region of ionized helium gas inside the galaxy. This was intriguing because such regions are far more common in very distant galaxies that existed shortly after the Big Bang, and those galaxies tend to have extremely low metallicity, meaning very few heavy elements. The ionization of helium occurs only when radiation is so strong that it can knock electrons away from helium atoms, leaving them charged. Such radiation usually comes from incredibly hot and powerful sources, far hotter than the ordinary massive stars that populate most galaxies today. This led scientists to a daring hypothesis. Perhaps Zwicki 18 contains a small number of Population 3 stars. Population 3 stars are a special theoretical group of stars thought to be the first ever formed in the universe. They would have been composed purely of hydrogen and helium, with no heavier elements at all. Because of their extreme heat and brightness, these ancient stars are believed to have lived short lives and died in massive explosions billions of years ago, long before our Milky Way even existed. Finding any trace of them today would be extraordinary, because they are thought to be extinct in the local universe. Yet, in Zwicki 18, the presence of helium ionization and the lack of metals suggest that such stars, or at least their close relatives, might still be forming there. If true, this would make Zwicki 18 one of the last surviving examples of the conditions that existed in the very early cosmos, almost like a living fossil from the dawn of time. Determining the true distance of Zwicki 18 was another major challenge. Astronomers at the Space Telescope Science Institute in Baltimore, Maryland, working together with the European Space Agency, decided to use a reliable method involving special stars called Cepheid variables. These stars are famous for their predictable rhythm of brightening and dimming, which occurs because they physically expand and contract over regular intervals. The time it takes for a Cepheid to complete one full pulsation cycle is directly related to its actual brightness. By comparing how bright these stars appear from Earth with how bright they truly are, astronomers can measure how far away they must be. In Zwicki 18, scientists managed to identify 3 Cepheid variable stars and observed their regular pulsations using the Hubble Space Telescope. They compared their observed brightness with theoretical models that were specifically designed for environments low in heavy elements like Zwicki 18. These models indicated that the stars in this galaxy formed during a time when heavier elements were still rare in the universe, confirming that the galaxy's stars were extremely old. To ensure accuracy, the team also compared these results with measurements of the brightest red stars in the galaxy, which were estimated to be older than 1 billion years. Both methods gave consistent results, showing that the galaxy's distance from Earth was about 59 million light-years. This distance turned out to be larger than scientists had first thought, and it helped explain why earlier observations had failed to detect the faintest, oldest stars inside the galaxy. The more distant an object is, the harder it becomes to resolve its individual stars, especially the dim ones. Because of this, the old stars in Zwicki 18 were almost at the limit of what Hubble could see. The newer and brighter blue stars, on the other hand, were much easier to detect, making the galaxy appear far younger than it truly is. The updated distance also helped clarify the galaxy's overall size, structure, and brightness, bringing a more complete understanding of its place in the universe. Zwicki 18 is classified as a dwarf irregular galaxy because it lacks the well-defined spiral or elliptical shape seen in larger galaxies. Instead, it appears somewhat chaotic, with clouds of gas and clusters of stars scattered unevenly across its body. It is also considered a blue compact galaxy, because most of its light comes from young, hot stars concentrated in its central regions, giving it a striking bluish colour. Furthermore, it is categorised as a starburst galaxy, because it is currently experiencing a period of intense star formation. Despite its small size, the rate at which new stars are being created inside Zwicki 18 rivals that of galaxies many times larger. In comparison with our Milky Way, which spans more than 100,000 light-years across, Zwicki 18 is incredibly tiny, only about 1.58 kiloparsecs in diameter, which equals roughly 5,150 light-years. Within this small space, the galaxy holds several clusters of young bright stars. Spectroscopic studies reveal that these stars are made almost entirely of hydrogen and helium, with barely any heavier elements at all. This composition is similar to that of the earliest stars that ever formed in the universe, and it is one of the reasons astronomers believe the galaxy may still be creating stars similar to those first-generation population 3 stars. When viewed through telescopes, the heart of Zwicki 18 glows with concentrated bluish-white light. This bright core contains 2 major regions where stars are forming at a furious pace. These regions are like stellar nurseries, filled with dense clouds of gas collapsing under their own gravity to give birth to new stars. Around these starburst centres, faint and wispy blue filaments extend outward into the surrounding space. These filaments are made of gas that has been blown away by the powerful winds from massive stars and by the violent explosions of supernovae, the deaths of stars that once burned fiercely in previous generations. These expanding shells of gas create an intricate network of bubbles around the galaxy's centre. The gas inside these bubbles is heated by the intense ultraviolet radiation pouring out from newborn stars, making it glow faintly in blue and ultraviolet light. Each new wave of star formation sends shock waves through the surrounding material, compressing it and creating more sites for future stars to form. In this way, the galaxy's history is written in overlapping layers of starbursts, each generation of stars shaping the conditions for the next. The view of Zwicki 18 through the Hubble Space Telescope is breathtaking in its detail. One can see clusters of young stars shining like tiny jewels embedded in a glowing sea of gas. The background space around it is filled with distant galaxies that appear as faint smudges of light, reminding us that this small system is part of a much larger cosmic tapestry. Its brilliant blue colour is not only beautiful, but also a direct sign of the presence of massive, short-lived stars that burn intensely and die young. These stars give off enormous amounts of ultraviolet radiation, lighting up the surrounding gas clouds and producing the luminous appearance that makes Zwicki 18 so distinctive. The galaxy's study has provided astronomers with valuable clues about how the first galaxies in the universe might have evolved. Because it contains so few heavy elements and is dominated by hydrogen and helium, it resembles the chemical makeup of the universe not long after the Big Bang. Observing Zwicki 18 therefore allows scientists to witness, in a sense, a living example of how early galaxies may have looked and behaved. It offers a window into the processes of star formation and chemical enrichment that transformed the universe from a simple, nearly uniform place into the rich and diverse cosmic landscape we see today. The continued study of Zwicki 18 using new technology, such as the instruments aboard the James Webb Space Telescope, promises to reveal even more about its hidden structure. Webb's ability to see through clouds of dust and capture faint infrared light could help astronomers uncover the oldest and most obscured stars that Hubble could not detect. It may also shed light on how the current burst of star formation began, and whether it was triggered by interactions with invisible dark matter or nearby gas clouds. Over the years, astronomers have come to see Zwicki 18 not just as an unusual dwarf galaxy, but as a cosmic time capsule. Its slow evolution, low metallicity, and repeated bursts of star formation provide an exceptional opportunity to study the earliest phases of galactic history still taking place in the modern universe. Each new observation reveals another layer of its complex life story, from its ancient beginnings billions of years ago to the brilliant blue fire of its present starburst era. Even though it occupies only a tiny corner of the vast universe, Zwicki 18 continues to fascinate scientists because it bridges two very different epochs of cosmic time. On one hand, it carries the chemical fingerprints of the primordial universe, while on the other, it displays the active star-forming energy typical of much younger systems. This strange combination makes it one of the most extraordinary laboratories for studying how galaxies are born, how they grow, and how the first stars once illuminated the darkness of space. The rings of the planet Uranus form one of the most fascinating and mysterious features in the solar system. In total, Uranus has 13 distinct planetary rings that encircle it. These rings are more complicated than the thin and simple rings around Jupiter and Neptune, yet not as large or detailed as the massive and brilliant ring system surrounding Saturn. The discovery of Uranus's rings marked one of the great surprises of modern astronomy and added a new dimension to our understanding of this distant and tilted world. The existence of these delicate rings was first confirmed on the 10th day of March in the year 1977 by three astronomers, James L. Elliott, Edward W. Dunham, and Jessica Mink. They made their discovery using the Kuiper Airborne Observatory while observing the planet as it passed in front of a distant star named SAO 158687. Their intention had been to study Uranus's atmosphere by observing how the planet dimmed the starlight, but what they noticed instead were 5 separate brief disappearances of the star's light, both before and after the main occultation by the planet. From this, they deduced that Uranus must be surrounded by a series of narrow rings that block the starlight momentarily as the planet moved in front of it. Long before this official discovery, more than a century earlier, the great British astronomer William Herschel, who had discovered Uranus itself, reported seeing what he believed might be rings around the planet. On the 22nd day of February in the year 1789, he noted in his observations, a ring was suspected. He even drew a small sketch showing the ring and described it as having a faint reddish tint. However, because the rings of Uranus are extremely dark and faint, modern astronomers have long debated whether Herschel could have possibly seen them with the telescopes of his time. The rings reflect very little sunlight. Their reflectivity, or bond albedo, is no more than 2%, which means they appear almost pitch black against the darkness of space. Herschel's old records were later published in the year 1797 in the Journal of the Royal Society. For nearly 2 centuries after that, hardly anyone mentioned Uranus's rings again. It was as if the idea had vanished into obscurity until the late 20th century, when new observations revived Herschel's old suspicion. Interestingly, modern instruments such as the Keck telescope in Hawaii have since confirmed that at least one of the rings, the Ena Onu ring, indeed appears to have a reddish hue, just as Herschel described more than 200 years earlier. By the time the rings were rediscovered in 1977, astronomers identified 9 distinct rings surrounding Uranus. Each of these was labelled with Greek letters A alpha, V beta, N gamma, D delta, and EM epsilon, based on the sequence in which the occultations occurred, along with additional rings numbered 4, 5 and 6, and another named Ites and ETA. Later, when the Voyager 2 spacecraft flew past Uranus in the year 1986, it captured clearer images of the system and revealed 2 more faint rings that had not been seen before. This brought the total to 11. Then, between the years 2003 and 2005, the Hubble Space Telescope detected 2 additional, more distant rings, increasing the total number known to 13. These new outer rings were much farther from the planet than the others, effectively doubling the previously known radius of the ring system. The rings of Uranus vary widely in brightness, structure, and composition. When arranged in order of increasing distance from the planet, the 13 known rings are named 1986 U2R. The closest ring, 1986 U2R or Z, lies roughly 38,000 kilometers from the planet's center, while the outermost ring extends to about 98,000 kilometers away. Between these main rings, astronomers believe there may be additional faint dust bands and incomplete arcs that have yet to be fully confirmed. The rings are composed of extremely dark material, likely a mixture of water ice, and small amounts of organic compounds that have been darkened by long exposure to radiation from space. These dark, radiation-processed organics absorb much of the light that reaches them, which is why the rings appear so dim even in strong telescopic views. Unlike the broad, dazzling rings of Saturn, Uranus's rings are narrow, dense, and composed mainly of relatively large particles, ranging in size from about 20 centimeters to 20 meters across. Some of the rings are opaque and only a few kilometers wide, while others, such as the faint 1986 U2R and N rings, are much thinner and consist primarily of fine dust particles. The narrow Lambda ring, although faint, contains both dust and larger fragments. One curious feature of Uranus's ring system is the relative lack of dust. Astronomers believe that this may be due to the planet's extended exosphere, a very thin outer atmosphere, which creates aerodynamic drag that gradually removes fine dust particles from the rings, leaving behind mostly larger bodies that are less affected by this drag. The rings of Uranus are thought to be relatively young compared with the age of the solar system. Scientists estimate that they are no more than about 600 million years old. This is quite young on cosmic timescales, suggesting that the rings were not formed during the planet's early history, but rather developed much later. One leading theory proposes that several of Uranus's smaller moons may have collided and shattered due to gravitational disturbances or impacts from comets or asteroids. The debris from those shattered moons could have spread out and eventually settled into narrow, stable bands that became the planet's rings. These rings have likely survived in their current form only in regions of maximum gravitational stability, where the particles are confined to narrow zones. Exactly what keeps these narrow rings so sharply defined remains one of the lingering mysteries of planetary science. When they were first discovered, scientists thought that every narrow ring must be shepherded and confined by 2 nearby moons, small satellites whose gravity keeps the ring particles from spreading out. Voyager 2's observations in 1986 confirmed that at least one such shepherd pair, Cordelia and Ophelia, does indeed keep the brightest ring, the E ring, neatly in place. Later, astronomers also found that the faint N ring is shepherded between 2 other moons, Portia and Rosalind. However, for most of the other rings, no obvious shepherd moons have been detected, leaving questions about how they maintain their narrow, sharply bounded structure. Over the centuries, the story of Uranus's rings has unfolded in stages, from Herschel's uncertain glimpse in the 18th century to the definitive discoveries of the late 20th century and the continuing observations of the 21st. In September of the year 2023, the James Webb Space Telescope captured one of the clearest and most detailed images yet of the Uranian ring system using its near-infrared camera. In that image, the faint dark rings appear as delicate shining loops surrounding the pale blue-green disk of the planet, offering humanity one of the most detailed looks ever obtained of this mysterious and remote world. The discovery in 1977 was a milestone in planetary science. It not only revealed the existence of another ringed planet besides Saturn, but also showed that ring systems might be a common feature in the outer solar system. Uranus thus became the second planet known to possess rings, inspiring a renewed interest in exploring the distant reaches beyond Jupiter. The coincidence that 5 years later, in 1982, all 9 known planets of that time, including Pluto, aligned on the same side of the Sun gave an even more poetic frame to this discovery. Every piece of evidence gathered since has continued to deepen the mystery of Uranus's rings. Their composition, their faint glow, their confined shapes, and their likely violent origins tell a story of destruction and renewal that still continues to unfold billions of kilometers from Earth. Even though they are among the darkest and faintest rings in the solar system, they remain one of the most hauntingly beautiful sights ever captured through the eyes of science, circling quietly around a distant tilted world in the cold twilight of the outer solar realms. The ring system of Uranus, as astronomers currently understand it, is made up of 13 distinct rings that circle the planet in a delicate and complex arrangement. Starting from the closest to Uranus and moving outward, these rings are known as 1986 U2R, sometimes called the Zeta ring, then rings 6, 5, 4, alpha, beta, eta, gamma, delta, lambda, epsilon, nu, and finally mu, which lies farthest from the planet. When scientists studied them more closely, they found that these rings could be grouped into 3 main categories. There are 9 narrow and clearly defined rings, 6, 5, 4, alpha, beta, eta, gamma, delta, and epsilon, then 2 rings that contain more dust, which are 1986 U2R and lambda, and finally 2 outer rings, nu and mu, that extend far from the planet into the surrounding darkness. Most of the material in these rings is made up of relatively large solid particles rather than fine dust. However, a few of the rings, especially 1986 U2R, ETA, delta, lambda, nu, and mu, do contain noticeable amounts of dust. Between the major rings, astronomers have detected faint thin bands of dust and barely visible ringlets that seem to appear and disappear over time. These fragile structures might exist only temporarily, breaking apart and reforming due to the gravitational pull of Uranus and its moons. Some of these faint bands were first noticed during a remarkable astronomical event in the year 2007, when the Earth passed through the plane of Uranus's rings, making them easier to detect. Earlier, when the Voyager 2 spacecraft visited Uranus in the year 1986, it saw several of these dust bands through the phenomenon of forward scattering, when sunlight reflects at a shallow angle and makes small particles easier to spot. Every one of Uranus's rings shows slight differences in brightness as they circle the planet, giving them a shimmering, uneven appearance when viewed through telescopes. The rings of Uranus are made of an incredibly dark material that reflects very little sunlight. Scientists estimate that their geometric albedo, the measure of how much light the ring particles reflect, does not exceed 5 or 6%, while the bond albedo, which includes all light scattered in all directions, is even lower, around 2%. This means the rings are darker than almost anything else in the solar system, absorbing most of the light that hits them. However, they do exhibit what astronomers call a steep opposition surge, meaning that when the sun is directly behind the observer, the rings suddenly appear much brighter. This happens because small shadows disappear and more light is reflected directly back. When viewed even slightly off this angle, their brightness drops dramatically. The colour of the rings is also unusual. They appear slightly red in ultraviolet and visible light, but turn grey when observed in the near-infrared spectrum. Their spectrum shows no clear chemical fingerprints, leaving scientists uncertain about what exactly they are made of. Because they are so dark, the rings cannot be made primarily of pure water ice, unlike the brilliant rings of Saturn. Instead, they are likely composed of a mixture of icy particles and some darker substance that makes them almost black. This dark material might be a type of organic compound that has been chemically altered by radiation from Uranus's powerful magnetic field. Over time, exposure to high-energy particles from the magnetosphere could have transformed originally bright ices into the dark, sooty material seen today. Many researchers think that the ring particles may once have resembled the material of Uranus's inner moons, but constant bombardment and radiation have changed their surfaces over billions of years, leaving them dull and lightless. Overall, Uranus's rings form a system unlike any other in the solar system. They are not as wide and brilliantly icy as the rings of Saturn, nor are they as faint and dusty as the ring system of Jupiter. They fall somewhere in between, dark, narrow, and sharply defined. Yet, there are some intriguing similarities between them and parts of Saturn's system. For instance, the narrow and relatively dark Epsilon ring of Uranus resembles Saturn's F ring. Both are thin and are kept stable by small moons, often called shepherd moons, that orbit just inside and outside them. The outer rings of Uranus, Nu and Mu, bear resemblance to Saturn's outer G and E rings, which are also faint and composed of fine dust. The thin dust bands that lie between Uranus's main rings may remind one of the faint, delicate rings surrounding Jupiter. The rings of Neptune share even more similarities. They're also narrow, dark, and contain more dust than Uranus's, but they lie farther from the planet and are simpler in structure. Among all the rings of Uranus, the Epsilon ring stands out as the most prominent and brightest. It is also the densest of all, reflecting about 2/3 of all the light coming from the entire ring system. Although it is the most eccentric of Uranus's rings, meaning its orbit is slightly elongated rather than perfectly circular, it remains almost perfectly flat, showing almost no tilt relative to the planet's equator. Because of its elliptical shape, its brightness changes depending on where it is along its orbit. When the ring reaches its farthest point from Uranus, called apoapsis, it shines more brightly, while at its closest point, called periapsis, it appears dimmer. The difference in brightness between these 2 points can be as much as 2.5 to 3 times. This variation happens because the ring's width also changes along its orbit. Near its narrowest point, the ring is only about 19 7/10 kilometers wide, while at its widest it stretches to about 96 4/10 kilometers. When the ring becomes wider, the particles are less crowded and cast fewer shadows on one another, allowing more sunlight to be reflected and making the ring appear brighter overall. Voyager 2's cameras were able to capture these differences clearly, as the Epsilon ring was one of only 2 rings visible in detail from the spacecraft's images. Observations from both Earth and space have shown that this ring is not optically thin, meaning it is dense enough to block and scatter a significant amount of light. Its optical depth, a measure of how opaque it is, varies between 0.5 and 2.5, being greatest when it is closest to the planet. The equivalent depth, which gives an idea of the total amount of material along a line of sight, is around 47 kilometers and remains constant around its orbit. The vertical thickness of the Epsilon ring has not been measured precisely, but scientists believe it is extremely thin, possibly only about 150 meters thick. Despite this, the ring is made of several overlapping layers of particles, suggesting a tightly packed dynamic structure. Near its widest point, the space within the ring is quite crowded, with the filling factor, meaning the fraction of space actually filled with particles, estimated to range from about 0.008 to 0.06. The average particle size within the ring varies between about 20 centimeters and 20 meters, with an average separation of roughly 4.5 times their radius. Interestingly, the Epsilon ring contains very little dust. This might be because small particles are quickly swept away by the thin outer atmosphere of Uranus, which creates a form of aerodynamic drag that removes them from orbit. Because of its incredible thinness, the ring becomes invisible when it is viewed edge-on from Earth. This happened in the year 2007 when Uranus's rings aligned with our planet's line of sight during a rare ring plane crossing event. Observations made by the Atacama Large Millimeter Array, or ALMA, revealed that the temperature of the Epsilon ring is about 77.3 kelvins, which is roughly minus 196 degrees Celsius. During the Voyager 2 mission, scientists detected an unusual radio signal when the spacecraft's instruments passed behind the Epsilon ring. The signal showed a strong increase in forward scattering of radio waves with a wavelength of 3 6/10 centimeters, especially near the ring's farthest point. This meant that the ring must have a finely organized internal structure that causes the waves to scatter in a coordinated way. Later observations confirmed this idea, showing that the Epsilon ring is not a uniform band but rather a complex system made up of many narrower ringlets, some of which may even be incomplete arcs. The Epsilon ring is kept in shape by 2 small shepherd moons, Cordelia on the inside and Ophelia on the outside. The inner edge of the ring moves in a delicate orbital resonance of 24 to 25 with Cordelia, while the outer edge is in a resonance of 14 to 13 with Ophelia. These gravitational relationships help keep the ring particles confined and prevent them from drifting away. For this to work, the the moons must each have a mass at least 3 times greater than that of the ring itself. Scientists estimate that the total mass of the Epsilon ring is around 10 to the power of 16 kilograms, an enormous amount of material held together by the planet's gravity and the careful guidance of its tiny moons. The delta ring of Uranus is almost perfectly circular, but slightly tilted from the planet's equatorial plane. Astronomers have noticed that this ring shows curious and unexplained changes in both its brightness and its thickness when observed at different angles around the planet. Some scientists believe this strange pattern may be caused by a small moonlet orbiting just inside the ring, creating wave-like disturbances as it moves. The sharp outer edge of the delta ring is linked to the Uranian moon Cordelia through what is called a 23-22 orbital resonance, meaning that for every 23 orbits made by particles in the ring, Cordelia completes 22. The delta ring is made up of 2 distinct parts. The first is a narrow, dense strip that is only about 4 to 6 kilometers wide and has a depth equivalent to a little more than 2 kilometers. This corresponds to an optical depth, a measure of how much light it blocks, of roughly 0.3 to 0.6, making it quite opaque. The second part is a broader inner region that is about 10 to 12 kilometers wide but much more transparent, with an optical depth of only about 3 times 10 to the power of -2. This means that this section allows most of the light to pass through. These details were not captured directly by Voyager 2's cameras, as they were unable to clearly resolve the delta ring. Instead, they were discovered through occultation experiments, where scientists observed how the ring dimmed starlight as Uranus passed in front of it. When Voyager 2 later viewed the ring in forward-scattered sunlight, meaning the sun was behind the ring, it appeared surprisingly bright. This suggested that fine dust particles were mixed into the wider, more transparent part of the ring. The broad component is also thicker in structure compared to the narrow one. Evidence from a ring plane crossing event in the year 2007 showed that the delta ring remained visible even when viewed edge-on, which fits the behavior of a ring that is thick but only lightly filled with material. The gamma ring, on the other hand, is narrow, dense, and slightly oval-shaped, though its tilt from Uranus's equator is almost 0. It is a tightly confined band, only about 3.5 to nearly 5 kilometers wide, but it has a constant optical depth equivalent of about 3 1/3 kilometers. Its normal optical depth, which shows how opaque it appears when viewed from above, is between 0.7 and 0.9. During the ring plane crossing in 2007, the gamma ring disappeared completely from view. This vanishing act revealed that it is very thin and contains almost no dust, much like the brighter Epsilon ring. Scientists also noticed that the gamma ring's width and brightness change at different points along its orbit. Although the reason this narrow ring remains so sharply defined is not fully understood, it has been found that its inner edge lies in a 6 to 5 orbital resonance with Uranus's moon Ophelia. This resonance might help maintain its structure. The Eta ring is almost perfectly circular and lies flat in Uranus's equatorial plane. Like the delta ring, it is made of 2 main parts. The first is a narrow and dense central band about 2 kilometers wide, with a depth equivalent to roughly 0.4 kilometers, giving it an optical depth of about 0.16 to 0.25. The second part is a much broader region extending about 40 kilometers outward, but it is far more transparent, with an optical depth near 2 times 10 to the power of -2. This ring was clearly captured by Voyager 2's cameras. When the spacecraft observed it in forward-scattered sunlight, the Eta ring appeared very bright, indicating the presence of fine dust particles, especially within the broader outer section. The broader part of the Eta ring is much thicker in vertical structure compared to the narrow core. This became clear again during the 2007 ring plane crossing, when the Eta ring shone more brightly than usual, becoming the second brightest feature among Uranus's entire ring system. This behavior confirmed that the Eta ring is geometrically thick but contains only a thin amount of material. Like most of Uranus's rings, it also shows irregular changes in brightness and thickness around its orbit, and in some places, the narrow core even disappears completely. The Eta ring also maintains an interesting connection with Uranus's moon Cressida. It lies close to what astronomers call a 3-to-2 Lindblad resonance with Cressida. This interaction causes the ring to develop a wavy pattern that has 3 bulges and 3 dips along its circumference. These move in rhythm with Cressida's orbit, creating a graceful rotating shape that circles Uranus at the same speed as the moon. After the brilliant Epsilon ring, the Alpha and Beta rings are the brightest parts of Uranus's ring system. Like the Epsilon ring, they both show steady changes in width and brightness depending on where they are in their orbit. They are brightest and widest at a point about 30 degrees from their farthest distance from Uranus, known as the apopsis, and they are dimmest and narrowest about 30 degrees from their closest point, the periapsis. Both rings have noticeable orbital eccentricity and slight tilts. The Alpha ring ranges in width from about 5 to 10 kilometers, while the Beta ring varies from about 6 to 11 kilometers. Their optical depths show that both rings are quite dense. The Alpha ring has an equivalent depth of roughly 3¼ kilometers and an optical depth between 0.3 and 0.7. The Beta ring's equivalent depth is about 2½ kilometers, with an optical depth of roughly 0.2 to 0.35. During the 2007 ring plane crossing, both rings vanished from view, confirming that they are very thin and contain little or no dust, similar to the Epsilon ring. Interestingly, that same event revealed a faint, wide and dusty band just beyond the Beta ring, something that Voyager 2 had also seen earlier during its flyby. Scientists estimate that the mass of each of these two rings is about 5 times 10 to the power of 15 kilograms, roughly half the mass of the large Epsilon ring. Closer to the planet, the rings known simply as Ring 6, Ring 5 and Ring 4 are the innermost and faintest of Uranus's narrow rings. These rings are more tilted and more elongated in their orbits than most of the others, except for the Epsilon ring. Their inclinations are about 0.06, 0.05 and 0.03 degrees respectively. These slight tilts were enough for Voyager 2 to capture them appearing above the planet's equatorial plane by roughly 24 to 46 kilometers. These three inner rings are also the narrowest in the Uranian system. Ring 6 measures about 1½ to 2 kilometers wide, Ring 5 about 2 to 5 kilometers, and Ring 4 roughly 2½ to 4½ kilometers. Their equivalent depths are about 0.4, 0.9 and 0.7 kilometers respectively, which translates into optical depths ranging from about 0.16 to 0.48. During the ring plane crossing in 2007, these inner rings were not visible at all, most likely because of their extreme thinness and their lack of dust. All these delicate structures around Uranus reveal a world of complexity hidden in what might appear, at first glance, to be simple, faint bands. Each ring tells a story of balance between gravity, motion, and time, shaped by resonances with moons, ripples from unseen moonlets, and the faint shimmer of dust reflecting sunlight across the distant reaches of the Uranian system. The Lambda ring, one of the most delicate and fascinating components of Uranus's ring system, was first discovered by the Voyager 2 spacecraft in the year 1986. It was one of 2 new rings found during that historic encounter. The Lambda ring is an extremely narrow and faint structure that lies just inside the bright Epsilon ring, positioned between it and the small shepherd moon known as Cordelia. This moon plays a role in shaping the region around the ring. It clears a thin, dark lane just inside the Lambda ring, helping to maintain its structure by gravitationally sweeping away stray material. When the Lambda ring is viewed in backscattered light, meaning when sunlight reflects off it toward the observer, it appears remarkably narrow, only about 1 to 2 kilometers wide. Its brightness, described through a property known as optical depth, is relatively small, between 0.1 and 0.2 kilometers when measured at a wavelength of 2.2 micrometers. What makes this ring particularly interesting is that its optical depth changes with wavelength, something quite rare among Uranus's rings. In the ultraviolet part of the spectrum, the ring's optical depth can reach as high as 0.36 kilometers, which is why Voyager 2 originally detected it only in ultraviolet light during stellar occultations. It was not until a decade later, in 1996, that astronomers announced its detection at infrared wavelengths of 2.2 micrometers, confirming that it was a distinct and dynamic feature of Uranus's complex ring system. The appearance of the Lambda ring changes dramatically depending on how it is illuminated. During Voyager 2's flyby in 1986, when it was observed in forward scattered light, meaning sunlight was shining through the ring material toward the spacecraft, the Lambda ring became the brightest structure in the entire Uranian ring system, even outshining the famous Epsilon ring. This sudden increase in brightness, along with its unusual wavelength-dependent optical depth, suggested that the ring contains a large amount of extremely fine dust particles, each only a few micrometers across. These tiny grains scatter sunlight very efficiently when viewed from certain angles, creating the intense brightness seen in forward scattered light. The normal optical depth of this dust is incredibly low, between 10 to the power of -4 and 10 to the power of -3, meaning the ring is almost transparent. Observations in the year 2007 by the powerful Keck telescope, made during a rare event when the ring plane of Uranus was seen edge-on from Earth, confirmed this behaviour. Once again, the Lambda ring shone as one of the brightest features in the system, proving that fine dust indeed dominates its composition. Detailed analysis of the images sent by Voyager 2 revealed that the brightness of the Lambda ring varies as one moves around it. These variations are not random. They seem to follow a repeating wave-like pattern that might resemble a standing wave encircling the planet. The cause of this strange and beautiful structure remains unknown, leaving scientists with yet another mystery about Uranus's delicate rings. During the same encounter in 1986, Voyager 2 also detected another faint feature, a broad, ghostly sheet of material located inside the innermost main rings. This feature was temporarily designated 1986 U2R. It had a very small optical depth of about 10 to the power of -3 or less, making it extremely difficult to see. At first, scientists believed it was visible in only one of Voyager's photographs. However, in the year 2022, a careful reanalysis of the old Voyager data revealed that this faint ring actually appeared in several post-encounter images. It was located between 37,000 and 39,500 kilometers from the center of Uranus, which means it floated only about 12,000 kilometers above the planet's cloud tops. After that discovery, the ring was not seen again until the early 2000s, when the Keck telescope observed a broad and faint band of material just inside what astronomers call Ring 6. This rediscovered feature was renamed the Zeta ring. Interestingly, the position of this Zeta ring differed from what Voyager had observed nearly 2 decades earlier. By the time of the Keck observations in 2003 and 2004, the ring was found between 37,850 and 41,350 kilometers from Uranus's center. Even more intriguing was a faint extension of material that stretched inward toward the planet, fading gradually as it approached the upper layers of Uranus's atmosphere. This extension reached at least as close as 32,600 kilometers, and perhaps even down to 27,000 kilometers above the planet's clouds. These inner extensions have been given the designation Zeta C and Zeta CC rings. The Zeta ring once again became a subject of fascination during the ring plane crossing event in the year 2007. When the sun shone through the rings at a very shallow angle, the Zeta ring became the single brightest feature in the entire Uranian ring system, shining even more intensely than the others combined. The equivalent optical depth of this ring was found to be about 1 kilometer, and roughly 1.5 kilometers for the inward extension. Its normal optical depth, however, was much lower, between 10 to the power of -2 and 10 to the power of -3. The ring also extended vertically over a height of about 800 to 900 kilometers above Uranus's equatorial plane. Scientists believe that the differences between the appearances of the 1986 U2R ring and the later Zeta ring could be explained by the different angles from which they were viewed. The Voyager observations in 1986 were made using side-scattered light, while the Keck and 2007 observations were made in back-scattered light. Nonetheless, it is also possible that over the course of 20 years, the distribution of dust within the ring has changed significantly, since dust is constantly being created and destroyed by collisions and radiation. Besides the Lambda and Zeta rings, the Uranian system contains several other incredibly faint dust bands that encircle the planet. These delicate ribbons of dust are so thin that they are almost invisible during occultation events, because their optical depths are negligible. Yet, when viewed in forward scattered light, they glow brightly, revealing their presence. Voyager 2's forward scattered light images first uncovered these hidden structures. They appeared as luminous streaks lying between the Lambda and Delta rings, between the Eta and Beta rings, and between the Alpha ring and Ring 4. Many years later, during observations made between 2003 and 2004, the Keck telescope detected these same dust bands once again. They also reappeared in backscattered light during the 2007 ring plane crossing event. However, their exact brightness and positions were not identical to those seen by Voyager. This indicates that Uranus's dusty ring environment is constantly evolving, influenced by subtle gravitational forces, radiation pressure, and impacts of tiny meteoroids. The normal optical depth of these faint dust bands is estimated to be around 2, give or take 3, and their vertical thickness is about 300 kilometers. The dust particles in these bands vary in size, following a distribution pattern described by what scientists call a power law. In this case, the size distribution follows an index of about 2.5, with a possible uncertainty of plus or minus 0.5, meaning there are far more tiny grains than larger ones. Beyond the visible rings and dust bands, the entire Uranian ring system appears to be surrounded by an even more diffuse and extensive veil of dust. This broadsheet is so faint that its normal optical depth does not exceed 10 to the power of -3, making it nearly transparent. It stretches all the way from the region of the Lambda ring inward toward the planet itself, forming a faint ethereal halo around Uranus. The vertical thickness of this dust sheet is about 140 kilometers, gently enveloping the inner regions of the ring system in a soft, dusty glow that is almost invisible to the human eye but still detectable to sensitive instruments. Together, these discoveries, first glimpsed by Voyager 2 in 1986 and later confirmed and expanded upon by the Keck telescope in the 21st century, show that Uranus's ring system is not just a collection of static rings, but a living and ever-changing structure. It is filled with fine dust, faint arcs, hidden bands, and complex variations that respond to light, gravity, and time in ways scientists are only beginning to understand. Between the years 2003 and 2005, the Hubble Space Telescope made a remarkable discovery around Uranus. It detected 2 previously unknown rings orbiting the distant planet. These newly found rings became known as the Outer Ring System, and their discovery increased the total number of Uranus's known rings to 13. Astronomers later gave them the Greek names Mu, SM, and Nu, Ion. The Mu ring is the farther of the two, lying at roughly twice the distance from Uranus as the bright Eta ring. Both of these outer rings are very different from the inner ones that were already known. While the inner rings are narrow and sharply defined, the Mu and Nu rings are wide and faint. The Mu ring stretches about 17,000 kilometers across, while the Nu ring spans roughly 3,800 kilometers. Despite their size, they are extremely dim, almost ghostly, with optical thicknesses so small that light barely reflects off them. Their brightness, when plotted, forms a triangular shape, which makes them stand out from the sharp-edged inner rings. Interestingly, the brightest point of the Mu ring lies almost exactly along the path of a tiny Uranian moon called Mab. Scientists believe that Mab is probably the source of the ring's material. Dust and particles may be knocked off the moon's surface by the impacts of micrometeorites and then spread out along its orbit, forming the ring. The Nu ring, on the other hand, lies between the orbits of 2 other moons, Portia and Rosalind, but it has no known moon within it. When astronomers re-examined old images taken by the Voyager 2 spacecraft, they noticed that the Mu and Nu rings became much more visible in light that had been scattered forward. This meant the rings contained large amounts of fine, micrometer-sized dust. The brightness pattern was similar to the faint outer rings of Saturn, especially the G and E rings. Saturn's E-ring, for example, is fed by dust from its icy moon Enceladus, and scientists think something similar could be happening with Uranus's Mu ring, with Mab as its main source. Further observations added even more clues. The Keck Observatory studied the rings in near-infrared light, focusing on a wavelength of about 2.2 micrometers. Interestingly, it detected the Nu ring but not the Mu ring. This suggested that the Mu ring reflects blue light, a sign that it is composed mostly of very fine sub-micrometer-sized dust grains. These tiny particles may be made of water ice, or ice mixed with other materials. In contrast, the Nu ring appeared slightly red, implying that its dust grains are larger or contain darker, less icy materials. A long-standing question about the Uranian rings is how they managed to remain so narrow and stable over time. Without some kind of force holding them together, their particles would gradually drift apart until the rings disappeared. Scientists estimate that without a stabilizing mechanism, Uranus's rings would disperse within 1 million years, which is a short time compared to the age of the planet itself. The leading explanation for this stability is something called the Shepherd Moon model, first suggested by researchers Peter Goldreich and Scott Tremaine. According to this idea, small moons located near the edges of rings act like shepherds, using their gravity to guide and confine ring particles. One moon pulls particles inward, while another pushes outward, keeping the ring in place. However, as they do this, the shepherd moons slowly drift away from the ring. For this mechanism to work properly, each shepherd moon must be at least 2 or 3 times more massive than the ring it controls. This process is already known to occur in Uranus's bright Epsilon ring, which is kept in check by 2 small moons, Cordelia and Ophelia. Cordelia also acts as the outer shepherd of the Delta ring, while Ophelia serves the same role for the Gamma ring. Beyond these, no moon larger than about 10 kilometers across has been found near other Uranian rings. Scientists have even used the current positions of Cordelia and Ophelia to estimate the age of the Epsilon ring, and their calculations suggest that this ring cannot be older than about 600 million years. Because the rings appear relatively young, scientists believe they must be constantly renewed. This renewal likely happens through collisions between larger bodies orbiting Uranus. Over time, impacts break these larger moons into smaller fragments, creating dust and debris that replenish the rings. Estimates show that a moon the size of Uranus's inner moonpuck could survive for a few billion years before being destroyed by collisions, but smaller moons would not last nearly as long. This means that over the planet's 4.5 billion year history, several moon-sized bodies may have been shattered, producing waves of debris that eventually formed the present ring system. Each of these destruction events would have triggered a chain reaction known as a collisional cascade, in which fragments collided again and again, grinding down into ever smaller pieces until only dust remained. Most of this material was eventually lost to space or absorbed by Uranus, but some particles managed to stay in stable orbits due to gravitational resonances and the guiding influence of shepherd moons. The result of billions of years of these processes is the narrow and delicate system of rings we see today. It is also likely that tiny moonlets, no more than about 10 kilometers wide, still exist within the rings, silently maintaining their shape and order. The presence of dust in the Uranian system is less mysterious. Dust grains have very short lifespans, anywhere between 100 and 1,000 years, because they are quickly pulled away or destroyed. Therefore, the dust we see must be constantly replaced. This happens when larger ring particles, small moons, or passing meteoroids collide, releasing fresh material into space. The main bodies that generate the dust are faint and practically invisible, but their existence is betrayed by the glow of the dust itself, which becomes visible in forward-scattered light. The main, narrow rings of Uranus and the dust bands surrounding them also differ in the types of particles they contain. The main rings are made up mostly of centimeter to meter-sized chunks, which reflect light efficiently, making them bright when seen in backscattered light. The dust bands, in contrast, contain far fewer large particles, so they appear much fainter. Recent observations made using the James Webb Space Telescope's near-infrared camera have revealed new details about the ring's composition. Among all of Uranus's rings, the Epsilon ring remains the brightest when viewed in infrared light between 1 and 5 micrometers. The rings labelled 4, 5, and 6, as well as the alpha, beta, eta, gamma, and delta rings, can be distinguished at shorter infrared wavelengths, but begin to blend together at longer ones. Spectral studies have shown that Uranus's rings absorb less light from water ice around the 3 micrometer wavelength than do the planet's smaller inner moons. This suggests that the ring particles contain less water ice on their surfaces, or that the particles are larger and less reflective. The farther a ring is from the planet, the stronger its water ice signal becomes, hinting that the outer rings might have a higher proportion of icy material. Some nearby moons, such as Mab and Puck, display unusual spectral patterns that may come from icy particles being exchanged between the rings and the moons themselves. These discoveries are helping scientists better understand how the Uranian rings formed, how they evolve, and how they interact with the small moons that share their mysterious region of space. In the month of January in the year 1986, the Voyager 2 spacecraft carried out a detailed investigation of Uranus and its mysterious system of rings. During its close encounter with the planet, this remarkable spacecraft made an exciting discovery: 2 new, faint rings that had never been seen before. These newly found rings were later named the Lambda ring, and the ring known as 1986 U2R. Their discovery increased the total number of Uranian rings known at that time to 11, revealing that Uranus's ring system was far more complex than scientists had once imagined. The Voyager 2 team studied these rings using several different scientific methods. The spacecraft carefully measured and analysed how radio waves, ultraviolet light, and visible light were blocked or dimmed as they passed through the rings, a technique known as occultation. By examining the data from these radio, ultraviolet, and optical occultations, scientists were able to learn important details about the structure, thickness, and composition of each ring. Voyager 2 also photographed the rings from many different angles, as the spacecraft, the planet, and the Sun change positions relative to one another. This allowed the rings to be seen in backscattered, forward-scattered, and side-scattered sunlight. In other words, the light reflected from the ring particles was captured from multiple directions. These varied views provided scientists with a complete understanding of how the ring particles reflect sunlight, known as their phase function. From this, they could also determine important physical properties, such as the geometrical and bond albedo, measurements that describe how bright or dark the ring particles appear when seen from different angles and how much sunlight they reflect overall. Among all the rings studied, 2 in particular, the Epsilon ring and the Eta ring, were captured in especially sharp and detailed images. These close-up views showed that the rings were not smooth or uniform, but were made up of intricate and finely detailed structures, including narrow bands and clumps that hinted at the presence of hidden forces shaping them. The photographs taken by Voyager 2 revealed even more surprises. Careful analysis of these images led to the discovery of 11 small inner moons orbiting Uranus. Among them were 2 tiny satellites named Cordelia and Ophelia, which were found to be the shepherd moons of the Epsilon ring. These moons act like cosmic guardians, keeping the ring's particles confined and preventing them from spreading out into space. The Horsehead Nebula, also called Barnard 33, is one of the most recognizable and fascinating sights in the night sky. This small but striking dark nebula lies within the constellation of Orion, one of the most famous constellations known to humankind. It is found just below the bright star Alnitak, which is the easternmost star in Orion's belt, the line of 3 bright stars that form one of the constellation's most familiar patterns. The nebula is part of a much larger structure known as the Orion Molecular Cloud Complex, a vast region filled with gas, dust, and newly forming stars. When astronomers look at this nebula through telescopes or in photographs, they immediately notice its distinctive shape. It looks remarkably like the head of a horse rising from a misty red glow. This remarkable form is what gave the nebula its name, the Horsehead Nebula. It lies inside a dense region of interstellar dust called LINS 1630, which is itself part of a larger active star-forming region known as IC 434. The whole area is a breathtaking part of our galaxy, where the process of creation, the birth of new stars, is happening before our eyes. The Horsehead Nebula is located about 422 parsecs away from Earth, which is roughly equal to 1,375 light-years. In cosmic terms, that distance is relatively close, allowing astronomers to study it in great detail. Despite being small when compared to giant nebulae such as the Orion Nebula, the Horsehead stands out because of its unusual dark silhouette and its mysterious beauty. Against the glowing red background of ionized hydrogen gas, its thick cloud of dust and gas forms the unmistakable outline of a horse's head, a sight that has fascinated astronomers, photographers, and dreamers alike for more than a century. The nebula's discovery has an interesting history. It was first noticed in the year 1888 by a remarkable Scottish astronomer named Williamina Fleming. She discovered it while examining a photographic plate taken at the Harvard College Observatory in the United States. Fleming was one of the pioneering women in astronomy during a time when science was mostly dominated by men. Her discovery was later recorded and described by the American astronomer Edward Emerson Barnard, who included it in his famous catalogue of dark nebulae as Barnard 33. He described it briefly but accurately as a dark mass about 4 arc-minutes wide, lying on a faint strip of glowing gas extending south from the star Zeta Orionis, which is another name for Alnitak. The region where the Horsehead Nebula is found is a busy and active one in astronomical terms. It belongs to the Great Orion Molecular Cloud Complex, a huge region of space where new stars are being born from dense clumps of cold gas and dust. When we look at Orion in the night sky, particularly during the winter months in the Northern Hemisphere, we're actually looking toward a rich and vibrant nursery of stars. For observers in the Southern Hemisphere, this same part of the sky is visible during summer evenings. No matter where one is on Earth, seeing Orion and knowing that such wonders lie within its boundaries adds a sense of mystery and wonder to the night sky. When colour photographs are taken of the Horsehead Nebula, it often appears surrounded by a deep red glow. This red colour comes mainly from hydrogen gas that has been ionised or energised by nearby bright stars. One of the key sources of this ionisation is the star Sigma Orionis, which shines powerfully in the region and causes the surrounding hydrogen atoms to glow. The glowing red light of hydrogen alpha radiation forms the background against which the dark shape of the Horsehead stands out so clearly. The nebula's shape is not solid but formed by intricate patterns of gas and dust, which are influenced by invisible magnetic fields. These magnetic fields guide and channel the flow of gases, shaping the nebula into long, delicate streams that appear as streaks in front of the bright background glow. At the very edge of the larger gas cloud IC 434, there is a sharp, bright strip of glowing hydrogen, marking the boundary between light and shadow. On one side of this border, the region is bright with glowing ionized gas, while on the other side, thick dust blocks the light, creating dark lanes. The number of visible stars also differs greatly between the two sides. There are noticeably fewer stars seen through the dusty region, as their light is heavily obscured by the interstellar material. The dark appearance of the Horsehead Nebula is mainly caused by its heavy concentration of dust. These particles of cosmic dust are so thick that they almost completely block the light from the stars and glowing gas behind them. Within the Horsehead region, as well as in nearby areas such as the Orion Nebula, the material is not evenly spread. Instead, it forms dense interstellar clouds separated by clearer regions. This creates a dramatic contrast of dark and light areas. Some parts are nearly opaque, while others are transparent enough to let starlight pass through. The base of the Horsehead, the area where the neck seems to join the main cloud, casts a dark shadow to one side, creating the impression of a solid, three-dimensional figure. But in reality, this head is made of cold gas and fine dust grains. The darkness and shape that we see are the result of the cloud blocking the brilliant red light coming from behind it. This simple but striking play of light and shadow gives the nebula its haunting and almost lifelike appearance. Inside this dark cloud, something extraordinary is happening. The Horsehead Nebula is not just a beautiful shape in the sky, it is a cradle of new stars. Deep within its obscured regions, small knots of gas and dust are collapsing under their own gravity, beginning the slow and powerful process of star formation. These young, forming stars are called protostars. They are still gathering mass and have not yet ignited the nuclear reactions that will make them shine fully. Some of the bright spots seen near the base of the Horsehead are these very young stars, celestial infants just starting to emerge from the surrounding cloud. Astronomers have also found that the Horsehead Nebula is rich in complex molecules, including those containing carbon, oxygen, and nitrogen, the basic ingredients of organic chemistry. The dust within it absorbs visible light but emits infrared radiation, which allows telescopes such as the Hubble Space Telescope and the James Webb Space Telescope to peer through its darkness and reveal the structures hidden inside. Observations in infrared light have shown narrow filaments, swirling gases, and small clumps where gravity is actively pulling matter together to form new suns. The Horsehead Nebula's existence inside the Orion Molecular Cloud Complex connects it to other famous astronomical objects in the same region, such as the Flame Nebula, NGC 2024, and the Great Orion Nebula, M42. Together, these form one of the richest and most studied star-forming regions in the entire Milky Way galaxy. The proximity of bright stars, glowing hydrogen gas, and dark dust clouds creates a breathtaking contrast that continues to captivate both professional astronomers and amateur sky watchers. Even though the Horsehead Nebula looks peaceful and still in photographs, it is actually a place of constant motion and change. Over time, the powerful radiation from nearby massive stars will slowly erode and disperse its shape. The gases that form the Horse's head are being heated, ionized, and pushed away by stellar winds. Eventually, perhaps millions of years from now, the familiar outline may disappear entirely, leaving behind the newly formed stars as the only trace of its former beauty. The Sombrero Galaxy, which is also known by several catalogue names such as Messier Object 104, M104, or NGC 4594, is one of the most eye-catching and mysterious galaxies ever observed. It lies on the borders of the constellations Virgo and Corvus, at a distance of about 9.5 megaparsecs, which equals roughly 31 million light-years from our own Milky Way galaxy. Astronomers classify it as a peculiar galaxy because it shows characteristics of both spiral and elliptical galaxies, making it difficult to place it in just one category. The Sombrero Galaxy belongs to a group of galaxies known as the Virgo II groups, a long chain of galaxies and clusters that stretch outward from the southern edge of the Virgo supercluster, one of the largest known galactic formations in the observable universe. In terms of size, the Sombrero Galaxy is quite impressive. Its diameter ranges from about 29 to 32 kiloparsecs, which means it spans between roughly 95,000 to 105,000 light-years across, making it just a little larger than the Milky Way. What makes this galaxy especially striking is its brilliant core, an unusually large central bulge, and a thick, dark lane of dust that wraps around the outer edge of its disk. Because we see it almost edge-on from Earth, this combination of a bright, bulging centre and a dark dust band makes the galaxy look just like a wide-brimmed Mexican hat, hence the name Sombrero Galaxy. When astronomers first observed this galaxy, they believed it was a typical spiral galaxy because its halo appeared to be small and faint. But later, the Spitzer Space Telescope revealed that the halo was actually enormous and far more massive than anyone had expected. This discovery suggested that the Sombrero Galaxy might instead be a type of giant elliptical galaxy, or perhaps a unique blend of both, a cosmic hybrid that stands between two galactic forms. The Sombrero Galaxy shines brightly in the night sky with an apparent magnitude of about +8, meaning that it is easily visible to anyone using a small amateur telescope. Some astronomers even suggest that it could be the brightest galaxy within a distance of 10 megaparsecs, or around 33 million light-years, from the Milky Way. Its immense central bulge, the presence of a supermassive black hole at its heart, and the beautifully defined dust ring make it one of the most studied galaxies in the universe. The discovery of this galaxy has an interesting story. It was first spotted on the 11th of May, 1781, by the French astronomer Pierre Méchain. 2 years later, in 1783, Méchain described it in a letter to the scientist J. Bernoulli, which was later published in a German astronomical yearbook. Around the same time, the famous astronomer Charles Messier made a note of the galaxy in his personal list of celestial objects, a list that would later become the well-known Messier catalogue. However, the galaxy was not officially added to that catalogue until the year 1921. In 1784, the English astronomer William Herschel also observed the same object independently. He noticed a dark stratum across its bright disk, which we now know as the dust lane that defines the galaxy's sombrero-like appearance. Later on, astronomers connected Herschel's and Méchain's observations, realizing they had been looking at the same remarkable object. In 1921, the French astronomer Camille Flammarion found Messier's handwritten notes referring to the galaxy, identified it with NGC 4594, and declared that it should officially be part of the Messier catalogue. Since then, this galaxy has been proudly known as Messier 104, or M104. The most striking feature of the Sombrero Galaxy is its dark, dusty ring that wraps around its bright bulge like a halo. This dust lane is not just a random band of material, it is actually a perfectly symmetrical ring that surrounds the galactic core. Within this ring lies most of the galaxy's cold atomic hydrogen gas and fine cosmic dust. Astronomers believe that it may also contain the majority of the galaxy's cold molecular gas, although this conclusion comes mainly from low-resolution observations, and more detailed studies are still needed to confirm it. Using infrared spectroscopy, scientists have discovered that this dusty ring is where most of the galaxy's star formation takes place. It is a cosmic nursery where new stars are slowly being born from clouds of gas and dust. At the heart of the Sombrero Galaxy lies an active nucleus classified as a low ionization nuclear emission line region, or LINER. In simple terms, this means that the gas in its central area is ionized, meaning that atoms have lost some of their electrons, but only weakly so. Scientists have long debated what powers this faint ionization. In some galaxies, it can be caused by hot young stars forming in the center, but in others, it is due to the intense radiation coming from an active galactic nucleus, the region surrounding a supermassive black hole. Observations in the infrared range show that there is little to no star formation occurring at the core of the Sombrero Galaxy. However, astronomers have identified a massive black hole in that very spot, leading them to conclude that this black hole is the main source of energy responsible for the weak ionization seen in the galaxy's nucleus. During the 1990s, a research team led by the astronomer John Comendi proved that the Sombrero Galaxy indeed contains a supermassive black hole at its center, using data from both the Canada-France-Hawaii telescope and the Hubble Space Telescope. They discovered that the stars near the center of the galaxy were moving at such high speeds that their motion could not be explained without the presence of an enormous mass pulling them inward. Their calculations showed that the object in the middle must have a mass of about 1 billion times that of our Sun. This makes it one of the most massive black holes ever detected in a nearby galaxy, and also the closest billion solar mass black hole to Earth. Further studies revealed that the core of the Sombrero Galaxy is also a powerful source of radio and X-ray radiation, a type known as synchrotron radiation. This happens when high-speed electrons spiral through strong magnetic fields, producing electromagnetic energy. Such emissions are typical of active galactic nuclei, regions where supermassive black holes feed on surrounding gas and dust. Interestingly, while the strength of this radio emission often changes dramatically over time in other galaxies, the Sombrero Galaxy's emission remains remarkably stable, varying only by about 10 to 20%. In the year 2006, two independent research groups made another fascinating discovery. They detected terahertz radiation, a form of electromagnetic energy between microwaves and infrared light, coming from the Sombrero Galaxy's core at a wavelength of about 850 micrometers. However, this radiation did not match any of the usual explanations. It was not caused by warm dust, nor by the typical synchrotron radiation, nor by emissions from hot gas or molecular clouds. The source of this strange radiation remains a mystery, adding yet another layer of intrigue to this already fascinating galaxy. The Sombrero Galaxy is known for having an unusually large number of ancient star clusters known as globular clusters, which are dense, spherical gatherings of thousands or even millions of stars. Astronomers have studied these clusters closely and estimated that the Sombrero Galaxy contains between 1,200 and 2,000 of them, an impressive number compared to most other galaxies of similar type. What makes this even more interesting is that the ratio of globular clusters to the total brightness of the galaxy is quite high. In simpler terms, for every bit of light the Sombrero Galaxy shines, it has more globular clusters than galaxies like our Milky Way or others with smaller central bulges. This abundance, however, is similar to galaxies that have large and bright central bulges. Because of this, astronomers believe there is a close link between the size of a galaxy's bulge and the number of globular clusters it contains. In fact, when scientists map how these clusters are spread out, they find that their density generally follows the brightness of the bulge. That is, the clusters become fewer as the galaxy grows dimmer, except very close to its shining core where the pattern changes. To understand just how far away this galaxy is, astronomers have used more than one clever method. The first method compares the light we receive from small glowing clouds inside the Sombrero Galaxy, called planetary nebulae, to the brightness of similar nebulae in our own Milky Way. Since we already know how bright the Milky Way's nebulae are, the difference tells us how far away the Sombrero Galaxy must be. This comparison gives a distance of about 29 million light-years, with a margin of error of around 2 million light-years, or roughly 8,890 kiloparsecs, give or take 610 kiloparsecs. The second method is known as the surface brightness fluctuation technique, which uses the texture of the galaxy's light to measure its distance. When a galaxy's bulge is close to us, we can see its stars as a kind of grainy pattern. But as the distance increases, that graininess smooths out, and the bulge appears like a soft glowing patch. By measuring how grainy or smooth the Sombrero Galaxy's bulge looks, astronomers can estimate its distance. The earliest measurements using this method suggested that it lies around 30.6 million light-years away, with an uncertainty of about 1.3 million light-years, or around 9,380 kiloparsecs, plus or minus 400 kiloparsecs. Later, after the method was improved, the estimated distance became 32 million light-years, with an error of about 3 million light-years, or about 9,810 kiloparsecs, plus or minus 920 kiloparsecs. Then, in the year 2003, further refinements gave an even more precise result of 29.6 million light-years, with a possible variation of 2.5 million light-years, or roughly 9,080 kiloparsecs, give or take 770 kiloparsecs. By combining all these findings, astronomers have calculated that the average distance to the Sombrero Galaxy is about 29.3 million light-years, with a margin of 1.6 million light-years, or approximately 8,980 kiloparsecs, give or take 490 kiloparsecs. The Sombrero Galaxy, also known as Messier 104, has an estimated mass of around 800 billion times the mass of our Sun. Its absolute magnitude in blue light, which tells us how bright it would appear if viewed from a standard distance, is measured at about minus 21.9, assuming the galaxy is around 30.6 million light-years away. If we use the average distance mentioned earlier, that figure becomes minus 21.8. These values make the Sombrero Galaxy the brightest galaxy within a radius of about 32.6 million light-years around our Milky Way, shining like a cosmic jewel in the vast darkness of space. In the year 2016, astronomers used the Hubble Space Telescope to refine the galaxy's distance once again, employing a more advanced technique known as the tip of the red giant branch method. This method examines the brightness of the oldest, reddest giant stars to determine how far away they are. The result gave a distance of about 9.55 megaparsecs, with two small margins of uncertainty, about 0.13 and 0.31 megaparsecs, making it one of the most accurate measurements so far. The Sombrero Galaxy does not exist in isolation. It lies inside a large thread-like cloud of galaxies that stretches southward from the famous Virgo cluster, forming a kind of cosmic filament that binds many galaxies together. However, astronomers are still unsure whether the Sombrero Galaxy truly belongs to a formal galaxy group. When scientists use hierarchical methods, which determine whether smaller galaxies are part of larger collections, the Sombrero Galaxy often appears to belong to a group that includes galaxies like NGC 4487, NGC 4504, NGC 4804, UGCA 289, and possibly several other faint companions. But when a different method called the percolation or friends of friends technique is applied, where galaxies are grouped based on their physical closeness and motion, results sometimes suggest that the Sombrero Galaxy may not belong to any group at all. In that case, it might instead form only a galactic pair with a smaller companion known as UK 287. In addition to these neighbouring galaxies, the Sombrero Galaxy is also accompanied by an extraordinary ultra-compact dwarf galaxy, discovered in the year 2009. This tiny companion is fascinating. It has an absolute magnitude of minus 12.3, meaning it is faint compared to normal galaxies, but still shines brightly for its small size. Its effective radius is only about 47.9 light-years, which equals roughly 3.03 million astronomical units, a mere speck in the cosmic scale. Yet despite its small size, it carries a mass of around 33 million times the mass of our Sun. Finding such a compact and massive dwarf near the Sombrero Galaxy has added another layer of mystery to this already intriguing galactic system. In the night sky, the Sombrero Galaxy can be found about 11.5 degrees west of Spica, the brightest star in the constellation Virgo, and about 5.5 degrees northeast of Eta Corvi, a star in the constellation Corvus. It can be seen even with simple optical instruments. With a pair of 7 by 35 binoculars or a small 4-inch telescope, about 100 millimeters in diameter, it appears as a faint elongated glow with a bright central core. However, to clearly see the galaxy's brilliant bulge separated from its wide disk, a telescope of around 8 inches, 200 millimeters, is needed. For observers who wish to admire the famous dark dust lane that gives the Sombrero Galaxy its striking hat-like appearance, a larger telescope of about 10 or 12 inches, 250 to 300 millimeters, is required. Dwarf 140 is a fascinating and powerful star system that has captured the attention of astronomers for many decades. It is not just a single star but a spectroscopic binary, meaning that two stars orbit each other so closely that even powerful telescopes cannot separate them visually. Their presence is instead revealed through the shifting of their spectral lines. The two stars that make up this system are very different yet equally extraordinary. One of them is an O-type star, an extremely hot and massive star with a brilliant blue-white glow, while the other is a Wolf-Rayet star, a rare and short-lived type of star that represents one of the final stages in the life of the most massive stars in the universe. While 140 lies within the constellation of Cygnus, the celestial swan high in the northern sky. If you were to look up and trace a triangle between the bright stars Deneb, Gamma Cygni, and Delta Cygni, you would find WR 140 shining faintly near the centre of that geometric figure. In July of the year 2022, the James Webb Space Telescope, using its powerful mid-infrared instrument, captured a breathtaking image of WR 140 surrounded by a spectacular nebula, vast clouds of dust glowing in delicate rings around the star. This image was more than just beautiful. It revealed vital clues about how certain kinds of stars produce and spread cosmic dust throughout the universe. WR 140 is considered a prototypical example of how cosmic dust is created. In this unique process, matter enriched with elements like carbon and silicon is periodically blown into space by stars nearing the ends of their lives. These dying giants, called Wolf-Rayet stars, lose their outer layers in fierce stellar winds that travel at thousands of kilometers per second. The outermost layers of a Wolf-Rayet star contain high concentrations of elements such as oxygen, nitrogen, silicon, and carbon, but are almost completely devoid of hydrogen. This unusual chemistry is one of the key reasons astronomers classify a star as Wolf-Rayet. Over time, these outer layers are expelled in repeating bursts or pulses. As the carbon-rich material moves farther away from the star, it begins to glow at a temperature of about 1000 kelvins. The intense ultraviolet radiation from the star heats the dust and causes it to shine in the infrared part of the spectrum. Telescopes like the James Webb can detect this infrared light, allowing scientists to study how the material expands and changes over time. This rebroadcasting of ultraviolet light by the carbon-rich dust creates the broad emission lines that define the unique spectral signature of a Wolf-Rayet star, in contrast to the more common absorption lines seen in ordinary stars. YAR 140 has long been described as the brightest Wolf-Rayet star in the Northern Hemisphere, although another star in Cygnus, known as BOR 133, rivals it in brightness. Even though the Wolf-Rayet component of the system dominates the spectrum, the O-type star is actually more massive and more luminous overall. Because of this, astronomers often refer to the O-type star as the primary and the Wolf-Rayet as the secondary, though both are remarkable in their own right. The O-type star is thought to be between type O4 and O5, likely a giant or even a supergiant, and detailed analysis suggests it may specifically belong to the class O5.5 Fc. The two stars of WR 140 follow a spectacularly elongated orbit that takes about 7 9/10 years to complete. Their path is highly eccentric, meaning they swing very close together at one point and then move far apart again. At their closest approach, called periastron, the two stars are separated by about 1 3/10 astronomical units, slightly more than the distance between Earth and the Sun. At their farthest point, known as a pastron, they drift apart to roughly 23 9/10 astronomical units, more than the distance from the Sun to Uranus. WR 140's brightness varies slightly over time, and because of these subtle fluctuations, it is classified as a Wolf-Rayet variable star under the name V1687 Cygni. The most dramatic changes occur around periastron every 8 years, when the two stars come closest together. During this time, their powerful stellar winds crash into each other, generating immense shockwaves and producing fresh bursts of dust. This causes a sudden brightening in infrared light, followed by a slow fading that lasts for several months. The collision of the stellar winds sculpts the dust into extraordinary shapes, spirals, arcs, and concentric shells that expand outward like ripples on a pond. The dust structures around WR 140 are more coherent and symmetrical than those around most other Wolf-Rayet systems, suggesting some hidden physical process within the Wolf-Rayet star itself may be influencing the pattern, perhaps related to activity deep in its nuclear burning core. Astronomers first observed the dust shells surrounding WR 140 between the years 1999 and 2001 using the Keck Observatory. From Earth, they could resolve only 1 or 2 faint shells, but when the James Webb Space Telescope turned its eye toward the system, it revealed an astonishing 17 distinct shells extending outward to about 45 arc seconds from the central stars. This corresponds to an incredible 70,000 astronomical units, so large that the outermost shells represent more than 130 years of dust production. A particularly bright feature within these shells, known as C1, has been used to study the mid-infrared spectrum of the dust. These observations revealed emissions likely caused by polycyclic aromatic hydrocarbons, complex carbon-based molecules that are extremely stable and often found in interstellar dust. This confirms that the material ejected by WR140 is rich in carbon and poor in hydrogen, matching the known composition of Wolf-Rayet outflows. Multiple observations with the Keck Observatory have also shown that the dust shells are not static. They are accelerating as they move outward, pushed by the powerful radiation from the stars. When the dust grains first form at about 50 astronomical units from the stars, they travel at roughly 1,810 kilometers per second. Over the next year, the radiation accelerates them by about 900 kilometers per second, until, at around 220 astronomical units, the dust becomes thinner and the acceleration slows down. With the help of both the Subaru and Keck telescopes, astronomers have detected this dust in both the mid-infrared and near-infrared wavelengths. The mid-infrared light corresponds to cooler and larger dust grains, with temperatures around 500 kelvins and sizes between 30 and 50 nanometers. The near-infrared emission, on the other hand, comes from extremely hot and tiny grains, only about 1 nanometer across, glowing at around 1000 kelvins. These minute particles are thought to form through violent grain-to-grain collisions or through a process known as radiative torque disruption, in which powerful radiation forces tear larger grains apart into smaller fragments. In the strange and fascinating system of WR140, two enormous stars, one of them a Wolf-Rayet and the other a Hotto-type companion, constantly interact through the immense power of their stellar winds. These winds collide and seem to shape dust into distinct curved bands that spiral outward into space. However, even though astronomers have studied this system for many years, they still do not fully understand how its many perfect circular shells of dust are formed. Some scientists believe that the answer might lie deep inside the Wolf-Rayet star itself, where the extreme nuclear reactions taking place in its core might be producing an unusually stable and rhythmic pattern in the dust it throws out into space. As the Wolf-Rayet star in WR140 reached the final stages of its brief but dramatic life, it began to run out of hydrogen, the fuel that keeps most stars shining. When the hydrogen in its core was finally exhausted, the powerful radiation pressure produced by hydrogen fusion began to fade. Without that inner pressure to counterbalance its own immense gravity, the star's outer layers started to collapse inward. The star shrank, its outer surface cooling while its core grew hotter and denser. This process of collapse did not continue forever, though. As the star's core compressed, the intense heat and pressure along its inner edge reached a point where helium fusion could begin. This new burst of nuclear burning released a flood of radiation that pushed outward, temporarily halting the collapse. The star swelled in size, but this was only a short-lived reprieve. The thin shell where helium fusion was taking place eventually expanded so much that the process slowed down or even stopped altogether. Without the steady energy of fusion, gravity once again took control, and the star began to collapse once more. Each time this happened, the outermost layers of the star's atmosphere were blown into space in a great outburst. Then, as the core heated up again, helium fusion restarted, briefly stabilizing the star until the cycle repeated. This rhythmic pattern of expansion and contraction, a sort of cosmic heartbeat, caused the star to shed layer after layer of gas and dust into the surrounding space. These layers became immense waves of material moving outward from the star, carried away by its fierce stellar wind at speeds of hundreds of kilometers per second. What astronomers now see as the beautiful concentric shells surrounding WR140 are the results of those long sequences of eruptions, yet it remains uncertain whether their strikingly regular spacing comes from the internal nuclear rhythms of the Wolf-Rayet star itself, or from the way its wind interacts with that of its O-type companion. Perhaps both factors work together to create this cosmic symmetry. Wolf-Rayet stars are among the hottest and most powerful stars known. Their surface temperatures can reach as high as 210,000 kelvins, making them shine fiercely in ultraviolet light. This intense radiation is strong enough to make 20 or even more distinct layers of dust visible to modern instruments. Astronomers have discovered that the distance between these shells matches the time between one pulse of helium fusion and the next, roughly 8 years. New shells of material have been seen forming in the years 1985, 1993, 2001, and 2009. Each new outburst marks another turn of this long cosmic rhythm. The distance between one shell and the next is astonishing, about 1 4/10 trillion kilometers. To imagine this more clearly, if our own Sun behaved like the Wolf-Rayet star in WR 140, one shell of dust would reach far beyond the icy bodies of the Oort cloud, almost 5% of the way toward the nearest star, Alpha Centauri, before the next shell was released. The James Webb Space Telescope has captured magnificent images of these dust rings, revealing how remarkably stable and regular they are. The intervals between the shells appear so consistent that they seem to continue unchanged for many decades, perhaps even hundreds of years. Each ring is a silent record of a dying star's heartbeat, a celestial rhythm that plays out across both time and space, marking the slow and graceful end of a once mighty stellar giant. Far beyond the bright spiral arms of our Milky Way, in the faint and mysterious outermost regions of our galaxy, the James Webb Space Telescope, NASA's most powerful observatory ever built, has turned its golden mirrors toward one of the most distant and quiet corners of our cosmic home. This region, known as the extreme outer galaxy, lies at an incredible distance of more than 58,000 light-years from the Milky Way's galactic center. It is a place where the familiar glow of the galaxy's central stars fades into the darkness of intergalactic space. Here, the night is quieter, colder, and thinner, filled mostly with scattered hydrogen gas, drifting dust, and rare pockets of star-forming clouds. For decades, astronomers have been curious about how stars are born in these distant, lonely regions, compared to the more crowded and active areas closer to the center of our galaxy. In the dense heart of the Milky Way, stars are born within huge, turbulent clouds of gas that are packed tightly together, their births influenced by the strong gravity, radiation, and pressure around them. But in the extreme outer galaxy, everything changes. The gas here is thinner, the metallic elements that help stars form are fewer, and the environment is much calmer. It is, in many ways, like looking back into an earlier time in the universe's history, when galaxies were young and the ingredients for star formation were still simple. To understand this rare environment, a group of scientists decided to study it using the powerful eyes of the James Webb Space Telescope. They pointed two of its most advanced instruments, the near-infrared camera, NIRCam, and the mid-infrared instrument, EMIRI, toward a collection of distant molecular clouds known as Diggle Clouds 1 and 2. These clouds, named after the astronomer Alan Diggle who first identified them, are among the outermost star-forming regions ever studied in our galaxy. Within these vast and cold clouds, astronomers chose 4 special areas where stars are currently forming, labeling them as 1A, 1B, 2 North, and 2 South. The James Webb Telescope, orbiting far from Earth, and equipped with instruments far more sensitive than any previous observatory, was able to peer through the thick layers of dust that normally hide these regions from view. In the past, even with the best infrared telescopes, these outer clouds appeared only as faint smudges of light. But now, for the first time, Webb's sharp vision revealed them in astonishing detail, glowing with the light of countless newborn stars still wrapped in the clouds that created them. One of the most fascinating of these regions is Cloud 2 South, often shortened to Cloud 2S. When Webb's cameras captured its image, scientists were amazed by what they saw. At the center of the view was a bright, shining cluster of newly formed stars. These stars, still very young in cosmic terms, are only a few million years old, infants compared to our own Sun, which is more than 4.5 billion years old. Many of these youthful suns are still actively growing, pulling in gas and dust from the surrounding cloud. In doing so, they release powerful streams of energy and material from their poles, long thin jets that shoot into space like cosmic fountains. These jets glow brightly in infrared light, allowing Webb to capture them in remarkable clarity. Each of these stellar jets marks the location of a star that is still forming, surrounded by a disk of swirling material that may one day give birth to planets. By studying these jets and the glowing gas around them, scientists can learn how stars develop in environments that are very different from those closer to the center of the Milky Way. But Webb's discoveries in Cloud 2S did not stop there. Near the top right of the main star cluster, astronomers found something even more exciting. A smaller subcluster of stars. This tiny cluster had been suspected for years, based on faint hints seen in earlier telescope images, but it was never confirmed. Now, Thanks to the incredible sharpness of Webb's instruments, its existence has been clearly proven. The stars in this subcluster appear to be at an early stage of formation, suggesting that starbirth in this region may happen in waves or sequences, one group of stars forming first and influencing the next generation nearby. This discovery is important because it helps scientists understand the timing and process of star formation in the galaxy's outskirts. In such remote areas, where the gas is thin and the conditions are more fragile, even small changes, like a shock wave from a nearby supernova or radiation from a cluster of young stars, can dramatically affect how new stars form. The presence of both a main cluster and a subcluster in Cloud 2s suggests that star formation can continue for long periods, spreading slowly through these clouds instead of happening all at once. Beyond the brilliant clusters of young stars, Webb's images revealed something else, a vast cosmic backdrop filled with faint glowing shapes. In the deep field of the image, scientists spotted a multitude of background galaxies, ancient, distant systems shining through the transparent parts of the cloud. Each of these galaxies lies millions or even billions of light-years beyond the Milky Way, their faint light crossing unimaginable distances to reach Webb's mirrors. Some appear as small spirals or fuzzy ellipses, while others look like tiny red dots, their light stretched by the expansion of the universe. Closer to the main cloud, the telescope also captured a complex web of reddish, glowing structures, nebulae made of gas and dust being shaped by the powerful winds and radiation coming from nearby stars. These winds push and sculpt the surrounding material into intricate patterns, carving out dark cavities and glowing ridges that make the entire scene look almost alive. The radiation from young, massive stars can heat and ionize the nearby gas, causing it to glow in the infrared wavelengths that Webb is designed to see. As a result, the telescope was able to reveal the true shape and depth of these nebulous regions in a way that was never possible before. For astronomers, each of these details provides vital clues. The color, brightness, and structure of the clouds tell scientists about their temperature, density, and chemical composition. The jets from the young stars reveal the strength of their magnetic fields and the rate at which they are gathering material. The faint background galaxies offer a distant contrast, helping to separate what belongs to our Milky Way from what lies far beyond it. Studying regions like the extreme outer galaxy is also a way of looking back in time, because these distant regions contain much less heavy material. Elements like carbon, oxygen, and iron that are produced inside stars, they closely resemble the conditions that existed when the universe was much younger. Billions of years ago, when the first galaxies began to form, star-forming clouds were made mostly of hydrogen and helium, with only tiny traces of other elements. The extreme outer galaxy therefore acts as a kind of natural laboratory for scientists who want to understand how the earliest generations of stars might have formed in the young universe. By comparing what they see in digital clouds 1 and 2 with what happens in regions closer to the centre of the Milky Way, scientists can test their theories about how star formation changes depending on the environment. In dense, metal-rich regions, starbirth can be fast and chaotic with powerful radiation and gravity shaping the clouds. But in the outskirts, the process is slower and quieter. The gas is colder and thinner, and stars form in small groups rather than huge clusters. Webb's ability to observe faint infrared light has made it possible to see these differences in exquisite detail for the first time. Every image that Webb captures adds another piece to the puzzle of how our galaxy, and galaxies like ours, build their stars over billions of years. The data from these observations are not just beautiful pictures. They are detailed measurements that allow scientists to estimate the masses of young stars, the temperatures of their surrounding clouds, and the timing of their formation. They help astronomers model how much gas remains to form future stars and how long the star-forming process might continue before the clouds are blown apart by stellar winds. When the James Webb Space Telescope was launched, one of its key goals was to explore how stars and planets form in different environments across the universe. These new images from the extreme outer galaxy show that Webb is achieving that goal far beyond expectations. They reveal not only the beauty of our galaxy's farthest regions, but also the underlying processes that connect the birth of stars today to the ancient past of the cosmos. The sheer distance of 58,000 light-years makes these observations even more remarkable. Light from these regions began its journey long before human civilization existed, travelling through the vastness of space until it was finally collected by Webb's instruments. What we see now is not what these regions look like today, but what they looked like tens of thousands of years ago. In a way, the telescope acts as a time machine, showing us snapshots from the distant past of our own galaxy. And yet, despite this enormous distance, the processes happening there, the collapse of clouds, the birth of stars, the outflow of jets, and the sculpting of nebulae, are the same natural mechanisms that once formed our Sun and the planets around it. In observing the extreme outer galaxy, we are in a sense looking at our own origins reflected back at us from the edge of the Milky Way. In the dark and ancient depths of the universe, long before the first stars of our own Milky Way were ever born, there existed a tiny, brilliant island of light that would one day astonish humankind. This ancient beacon is now known as JD's GSZ 14-0, a galaxy so distant that the light we see from it began its journey when the universe itself was still in its infancy. This galaxy lies in a small and faint southern constellation called Fornax, whose name means the furnace. It was discovered in the year 2024 using one of the most extraordinary instruments ever built by human hands, the James Webb Space Telescope, often called JWST. JADE's GSZ 14-0 is what astronomers describe as a high redshift Lyman break galaxy. This description might sound complicated, but it simply means that the galaxy is seen so far away that the light it gives off has been stretched into redder wavelengths as it travelled across expanding space. When light from distant objects travels through a universe that has been expanding since the Big Bang, its colour shifts toward the red end of the spectrum, a phenomenon known as redshift. The higher this redshift number, the farther away the galaxy is, and the longer its light has travelled through time to reach us. The redshift of JD's GSZ 14-0 is an astonishing 14.18, one of the largest ever recorded for any galaxy or celestial object. What that means is that the light from this galaxy left it around 13.5 billion years ago, when the universe was only about 300 million years old, a mere 2% of its present age. To put this into perspective, if the history of the universe were condensed into a single year, with the Big Bang happening on January 1st and today being December 31st, then JD's GSZ 14-0 would have existed around the 2nd or 3rd day of January, so early that cosmic dawn had only just begun. The galaxy was first noticed through the Near-Infrared Camera, or NIRCam, aboard the James Webb Space Telescope. This camera was part of an ambitious project called the JWST Advanced Deep Extragalactic Survey, known more simply as JDES. This program was designed to explore the earliest and faintest galaxies in the farthest reaches of space, seeking to understand how the first cosmic structures emerged from the darkness following the Big Bang. The discovery of JD's GSZ 14-0 was one of the program's most exciting achievements, because it offered an actual glimpse of one of the first galaxies ever to form in the universe. Later in the same year, the galaxy was observed again using another instrument on the telescope, the Near-Infrared Spectrograph, or NER spec. This instrument does more than just capture images. It can separate light into its different wavelengths, allowing scientists to measure the redshift precisely and to learn about the galaxy's composition. NERSpec confirmed that JD's GSZ 14-0 had an even more precise redshift value of 14.32, reinforcing its place among the most distant galaxies ever seen by human eyes. The light of this galaxy carries a story from the universe's earliest age. Its brightness, size, and the way it shines tell astronomers that their theories about the formation of the first stars and galaxies might still be incomplete. For a long time, scientists believed that the early universe was a slow and gentle place, with tiny clumps of hydrogen gas gradually forming small, faint galaxies. But the existence of a luminous and massive galaxy like JD's GSZ 14-0 only 300 million years after the Big Bang suggests something different, that some galaxies grew quickly, and that the universe's first generations of stars might have been far more active and energetic than expected. A larger study was later carried out under the title Earliest Galaxies in the JADES Origins Field, Luminosity Function and Cosmic Star Formation, Rate Density 300 million years after the Big Bang, led by an astronomer named Robertson, and published in 2024. This study analysed many early galaxies discovered by JWST and found that JD's GSZ 14-0 had a photometric redshift, an estimate based on colour and brightness, of 14.39 with only a small margin of uncertainty. Such consistency between measurements confirmed the extraordinary distance of this galaxy and strengthened the conclusion that it truly existed when the universe was only a few 100 million years old. JD's GSZ. 14.0 is not a giant in size, at least not compared to modern galaxies like our Milky Way. It spans about 1,600 light-years across, which is small next to the Milky Way's 100,000 light-year width. Yet, for its era, it was a powerhouse of light, a bright, compact and lively system where countless young stars were forming at a remarkable rate. Spectroscopic analysis revealed the glow of ionized hydrogen and oxygen gas, both clear signs of active star formation. This means that even in the universe's first few 100 million years, some galaxies were already creating complex elements and lighting up the young cosmos with brilliant energy. The discovery began with delicate and patient imaging work by JWST's near-infrared camera, which is designed to look deep into the distant universe by observing wavelengths of light that the human eye cannot see. As astronomers examined these images, they noticed a faint but consistent source of light in the data, an object that seemed to vanish in shorter wavelengths, but glowed brightly in the longer infrared range. This was the Lyman break feature, the signature that tells astronomers they are looking at an extremely distant galaxy whose light has been stretched by the expanding universe. To verify that the object was indeed a faraway galaxy and not something else, such as a star or a nearer galaxy covered in dust, astronomers used JWST's NER spec to gather detailed spectra, the fingerprints of light that reveal both distance and composition. The spectroscopic observations matched perfectly with what scientists expected for a galaxy whose light had travelled from nearly 14 billion years ago. To strengthen their case even further, they observed it again using JWST's mid-infrared instrument, called MIRI, which is capable of detecting longer wavelengths of light. These additional observations showed that the galaxy's light continued smoothly into the mid-infrared range, providing firm evidence that JD's GSZ 14.0 was indeed located at an incredible distance. By the early months of the year 2025, another important study appeared, titled Photometric Detection at 7.7 micrometers of a galaxy beyond redshift 14 with JWST MIRI. This work, led by Helton and others, combined observations from both MIRI and NIRCam. The mid-infrared data provided an even more detailed look at the galaxy's light, revealing strong emission features that are particularly useful for studying its chemical composition. According to this study, JD's GSZ 14.0 might contain roughly 500 million times the mass of our Sun, meaning that by the time the universe was only 300 million years old, this galaxy had already gathered an enormous amount of material and converted much of it into stars. The authors of that study noted that the existence of such a massive and luminous galaxy so early in cosmic history was not expected according to older models. Before JWST, astronomers had used telescopes such as the Hubble Space Telescope to estimate how many bright galaxies existed in the young universe, and they believed such large ones were extremely rare. But the findings from JD's GSZ 14.0 and other similar galaxies discovered by JWST suggested otherwise, that the number of these early bright galaxies was at least 10 times greater than anyone had predicted. This meant that star formation in the early universe must have been a much faster and more efficient process than scientists had previously imagined. Then, in the same year, 2025, another stunning discovery followed. Astronomers managed to detect oxygen in the galaxy JD's GSZ 14.0, marking the farthest observation of this element ever made. This was achieved with the help of an entirely different observatory on Earth, the Atacama Large Millimeter-Submillimeter Array, known as ALMA, located in the high and dry Atacama Desert of northern Chile. ALMA is an array of dozens of radio telescopes that work together to observe the faint, cold light emitted by molecules and atoms in space. Detecting oxygen in such a distant galaxy was a tremendous achievement, because oxygen is not one of the primordial elements formed immediately after the Big Bang. Instead, it is created inside stars and released into space when those stars die. This means that by the time we see JD's GSZ 14.0, only 300 million years after the universe began, it had already formed and destroyed several generations of stars, enriching its gas with oxygen and possibly other heavier elements. This discovery changed the way scientists think about the early universe. It showed that galaxies at that time could evolve and mature far faster than anyone expected, producing chemical complexity that was supposed to take billions of years to appear. The detection of oxygen was therefore more than just a measurement. It was a message from the dawn of time telling us that the cosmos grew up quickly, blazing with creativity in its earliest days. Furthermore, this detection allowed astronomers to refine their understanding of how far away JD's GS Z14-0 really is. ALMA's precise instruments measured the galaxy's redshift at 14.1793, with an uncertainty of only about 0.0007, an incredibly tiny margin of error, less than 1 part in 20,000. This level of precision confirmed beyond any doubt that the galaxy truly belongs to the epoch known as Cosmic Dawn, the period when the first stars and galaxies illuminated the universe's darkness. The detection of oxygen by ALMA was soon supported by 2 major research teams, led by S. Carniani and S. Skoos. Both teams published their findings in 2025, presenting spectroscopic data that aligned almost perfectly with previous measurements. The ALMA redshift value of 14.1793 was consistent with earlier tentative detections of carbon in the same galaxy. Those earlier observations, made with JWST in the previous year, had measured carbon at a redshift of 14.178, almost identical to the oxygen result. The close agreement between these independent measurements gave scientists strong confidence that they were seeing the same galaxy and that their distance calculations were accurate. By combining all this evidence, the data from JWST's NIRCam, NIRSPEC and MIRI instruments, as well as the results from ALMA, astronomers could paint a vivid portrait of JD's GS Z14-0. It was a small, compact and luminous galaxy filled with young stars, glowing clouds of gas, and traces of heavy elements like carbon and oxygen. It was a place of tremendous activity, where stars were forming rapidly, heating up the surrounding gas and making it shine with the light we can still detect, after nearly 14 billion years of travel through space. The story of this galaxy is more than a single scientific discovery. It is a glimpse into the earliest chapters of cosmic history. The light from JD's GS Z14-0 began its journey long before our own solar system, Earth, or even the Milky Way existed. It travelled across the expanding fabric of space, crossing billions upon billions of light years, until finally, in our time, it reached the sensitive instruments of the James Webb Space Telescope. When astronomers first saw its faint glow in their data, they were not just looking at a distant galaxy. They were witnessing the past itself, preserved in light that had been moving since the dawn of time. The galaxy's properties also reveal something remarkable about the speed of cosmic evolution. If JD's GS Z14-0 already contained hundreds of millions of solar masses worth of stars and had produced oxygen and carbon, then the process of star formation must have begun almost immediately after the Big Bang. The first stars, sometimes called population 3 stars, were likely enormous, bright, and short-lived. They would have lived for only a few million years before exploding as supernovae, scattering heavier elements like carbon, oxygen, and nitrogen into surrounding space. These materials would then be used to form the next generation of stars, gradually building up galaxies like JD's GS Z14-0. Thus, within a remarkably short time after the Big Bang, perhaps only 100 or 200 million years, the universe already contained enough structure and material for galaxies to shine brightly. This challenges the older view that it took much longer for large galaxies to form. The data from JWST and ALMA now suggest that galaxy formation was rapid, efficient, and widespread. The early universe was not a quiet, dark place, but rather a busy and creative one, bursting with light and motion. Jade's GS Z14. 0 then stands as a symbol of this early cosmic vitality. It is not merely a distant object frozen in the past. It is a story written in starlight, a record of the universe learning how to create itself. The discovery of such a galaxy shows us that even in the universe's youth, nature was already capable of astonishing complexity. It also teaches us humility, reminding us that there is still much about cosmic origins that we do not yet understand. Scientists continue to study this galaxy with every tool available, hoping to learn more about its stars, its dust, and the processes that gave rise to it. Every new observation adds another piece to the puzzle, of how the first galaxies formed and evolved. Future instruments, perhaps the next generation of telescopes beyond JWST, may reveal even earlier galaxies, pushing our view closer and closer to the actual moment when the first stars ignited. But for now, JAID's GSZ 14-0 represents one of the most distant and ancient beacons humanity has ever found.